Close your eyes for a moment. Imagine a continent that does not yet have a name. No borders, no roads, no cities, no monuments, just land. Ancient land, stretching from horizon to horizon, under a sky that has never once been crossed by anything with wings. The air is warm and thick and smells of wet earth and flowering fern. Somewhere in the middle distance, a river winds through a floodplain so flat and so wide that you could walk for 3 days and barely notice you had moved. And along that river, enormous shapes are moving, not quickly, not frantically, slowly, deliberately, the way things move when they have never once needed to hurry. These are the Americas before they were the Americas, and the creatures walking their floodplains are unlike anything alive today. This is the story of the real Jurassic Americas. If you enjoy listening to sleepy prehistoric dinosaur stories like this, subscribe. I post stories like this weekly. Let's begin where everything begins, with the land itself. Before we can talk about the dinosaurs that lived across the ancient Americas, before we can walk through the forests of Jurassic North America or stand on the sun-baked plains of Jurassic South America, we need to understand something fundamental about the world those dinosaurs lived in. Because the Americas, as we know them today, did not exist during the Jurassic period. The familiar shapes we see on maps, that long joined landmass stretching from the Arctic tundra down to the tip of Patagonia, that shape did not exist yet. The world in which the Jurassic dinosaurs of the Americas lived was so different from the world we know that calling it by the same name feels almost misleading. To understand where the Americas came from, we need to go back even further than the Jurassic period itself. We need to go back to the late Triassic, roughly 230 to 200 million years ago, when the landmass that would eventually become North and South America was still part of the ancient supercontinent called Pangaea. The word Pangaea means all Earth, and that name is not poetic license. It is a description of geological fact. During the Triassic period, nearly all of Earth's landmass was fused together into one colossal continent that stretched from pole to pole, surrounded on all sides by the vast Panthalassic Ocean and its subsidiary seas. Pangaea was extraordinary in its extremity. The interior of this supercontinent was a place of brutal conditions. Because moisture-laden air from the oceans could only penetrate so far inland before losing all its water, the deep interior of Pangaea was a desert of almost incomprehensible scale. Not the picturesque red sand deserts of the modern American Southwest, but something far more barren, a geological wasteland of wind-scoured rock and compacted sediment, where temperatures swung between lethal heat during the day and biting cold at night. The heart of Pangaea was, in most respects, as inhospitable as any place on Earth has ever been. But the margins of this great continent were different. Along the coastlines where ocean winds still carried moisture, and in the river valleys and deltas where fresh water drained down from ancient highlands, life found a foothold. And what life it was! The late Triassic world, the world that immediately preceded the Jurassic, was alive with a diversity of creatures that we are only now beginning to fully appreciate. These were the years immediately following the Carnian pluvial episode, that extraordinary 2 million year period of almost constant rainfall that we have explored in other stories on this channel. In the aftermath of all that rain, the world had been restructured. Old dominant groups had gone extinct. New ones were rising, and in the southern reaches of Pangaea, in the region that would eventually drift westward and southward to become South America, something remarkable was stirring. The land that would become South America during the Triassic period occupied a very different position on the globe than it does today. Plate tectonics, the slow and inexorable movement of the great crustal plates that make up Earth's outer shell, had positioned what would become South America in a location closer to the equator, connected directly to Africa on one side and to what would become North America on another. This region of Pangaea, roughly corresponding to the modern South Atlantic and the eastern coast of South America, was wet enough to support forests. Primitive conifers grew tall along ancient river systems. Seed ferns, those distinctive plants with their divided fronds, spread across the forest floor. Cycads, ancient seed plants that looked something like modern palms but were utterly unrelated to them, grew in clusters along the edges of seasonal lakes. It was a lush world by Triassic standards, not the deep green exuberance of a modern tropical rainforest. Flowering plants had not yet evolved, and would not for another 100 million years. There was no grass, no fruit, no bright blossoms swaying in the breeze, but there was green, and where there is green there is life, and where there is life there is complexity. And in the undergrowth of those ancient Triassic forests, something small and quick and surprisingly promising was moving. The very first dinosaurs were here, in this southern portion of Pangaea, in what would eventually become northwestern Argentina. They were not impressive by dinosaur standards. By the standards of everything else alive at the time, the dominant creatures were the Rossuchians, massive crocodile-like predators, some of which grew to the size of large trucks. There were the Etosaurs, heavily armoured herbivores that looked something like heavily modified alligators walking on slightly longer legs. There were the cynodont therapsids, the advanced mammal-like reptiles that were already developing some of the features we associate with true mammals. In this world, the earliest known dinosaurs were small. Some were barely larger than a domestic cat. Others were the size of a large dog. They were bipedal, moving on two legs with their tails held out behind them for balance. They had hollow bones. They had grasping hands. They had eyes positioned well forward in their skull, giving them better depth perception than many of their competitors. And they were positioned at exactly the right place at exactly the right moment in Earth's history. The late Triassic world in which those first dinosaurs lived was defined by its inconsistency. After the Carnian pluvial episode ended, the climate of the late Triassic became increasingly variable. Wet periods alternated with dry ones. River systems that ran broad and full during the rainy season shrank to trickles during drought. This boom and bust pattern was hard on specialists. Animals perfectly adapted to a specific food source or a specific habitat type struggled when that habitat disappeared or changed. But generalists, animals that could eat a variety of foods and survive in a variety of environments, those animals thrived. The earliest dinosaurs were generalists almost by definition. They were omnivores, or at least highly flexible carnivores. They could eat insects, small vertebrates, eggs, carrion, possibly some plant material. When food disappeared in one area, they could move. Their bipedal locomotion, legs positioned directly under their bodies in the upright posture, rather than sprawling out to the sides as in most other reptiles, made them unusually efficient movers. They could cover ground while burning relatively few calories. This efficiency was not glamorous. It did not make them apex predators or dominant herbivores, but it made them survivors. And in the late Triassic world, where conditions could change rapidly and dramatically, being a survivor was the most important thing you could be. The region of Pangaea that would become South America was particularly important to early dinosaur evolution, for reasons that geologists are still working to fully understand. The Isigualasta Formation, the ancient geological unit exposed in what is now the remote desert of northwestern Argentina's Isigualasto Provincial Park, preserves one of the most extraordinary windows into this pivotal moment in life's history. The rocks of Isigualasto, sometimes called the Valley of the Moon by those who have seen its otherworldly landscape of grey and lavender badlands, were laid down roughly 231 million years ago. And in those ancient sediments, paleontologists have found the bones of creatures that stand at the very root of the entire dinosaur family tree. But we're getting ahead of ourselves slightly. Before we meet the specific animals that lived in these ancient landscapes, we need to finish setting the stage. We need to understand what the world looked like, what it felt like, what it smelled like in those years before the Jurassic Period began. Imagine standing in what would eventually become northwestern Argentina, 230 million years ago, in the late afternoon of a day in the wet season. The air is warm, perhaps 30 degrees Celsius, but not unbearably so. There is humidity here, the lingering moisture of recent rains, and the atmosphere carries the sweet green smell of a living vegetation, mingled with the dark, rich smell of wet soil. Before you stretches a floodplain, broad and flat, its surface a complex mosaic of dried mud cracked into polygons by the sun, shallow standing pools left by the last flood, and patches of low-growing vegetation. The vegetation is strange to modern eyes. There are no grasses, no flowering wildflowers, no familiar leafy shrubs. Instead, the ground cover consists of sprawling ferns and horsetails, their stems thick and hollow, their fronds casting minimal shade over the sun-warmed earth. Further back from the floodplain, where the ground rises slightly and drainage is better, the landscape changes. Here, primitive conifers grow in loose stands, their silhouettes not quite like any tree alive today, their canopies sparser, their branches arranged in wider, flatter tiers than a modern spruce or pine. Between these trees, cycads grow in clusters, their thick trunks rising to crowns of stiff, outward-pointing fronds. The forest floor beneath them is dim and cool, carpeted with decaying plant matter and the occasional splash of fern green. The sounds of this world are familiar and unfamiliar simultaneously. There are insects. There are always insects. And by the late Triassic, they have already been evolving for over 200 million years. The rhythmic sawing of ancient crickets, the hum of early beetles in flight, the brief sharp sounds of dragonfly-like insects moving through the undergrowth. These sounds are not so different from the insects of a modern forest, but there are no bird calls. There are no mammal rustlings in the undergrowth, at least not mammal rustlings as we would recognize them. The small furry things that move in the leaf litter are not true mammals yet. They are the advanced cynodonts, the mammal-like therapsids, and their sounds, if we could hear them, would be slightly different from the sounds of modern rodents. And then there is the river. Behind you, wide and slow-moving in the season between floods, the river that drains this ancient landscape moves toward the interior of Pangaea. It is the colour of weak coffee, carrying suspended sediment from upstream. Along its banks, the vegetation is thicker and more diverse. In the shallows, strange amphibian creatures bask on exposed mudbanks, their flattened heads and splayed limbs identifying them immediately as something archaic, even by the standards of their own time. Temnospondyls, large predatory amphibians that had survived the Permian extinction, still occupied the riverbanks of the late Triassic world, though their dominance was fading. And then, moving along the edge of the floodplain in the middle distance, there is a shape that is different from everything else. Bipedal, quick-moving. Its tail carried straight and horizontal behind it, acting as a counterbalance for its forward-leaning body. It is small, perhaps 1.5 meters long from nose to tail tip, and it moves with a particular quality of alertness that sets it apart from the heavier, more lumbering creatures of this world. It pauses, turns its head, looks at something in the undergrowth with large forward-facing eyes. Then it darts forward, and a brief flurry of motion ends with a small prey item being swallowed. That creature is a dinosaur. It is among the earliest of its kind. It does not know that its descendants will one day weigh 80 tons and shake the ground with each step. It does not know that its lineage will dominate this planet for the next 165 million years. It is simply a small, quick, hungry animal, doing what small, quick, hungry animals do, surviving one meal at a time in a world that does not particularly care whether it lives or dies. But it will live, and its lineage will flourish. Now let's understand what happened next. Let's understand how this small, marginal creature, in this warm, wet corner of the ancient supercontinent, set in motion one of the most extraordinary chapters in the history of life on Earth. Let's go to the beginning, to the cradle of the dinosaurs, to the place where the entire Jurassic Americas story started. Some discoveries change everything, not in the dramatic sense of a sudden revelation, but in the slow, accumulating sense of a picture gradually coming into focus. The story of how paleontologists discovered the birthplace of the dinosaurs in South America is exactly this kind of story. It is the story of patient work in some of the most remote and inhospitable terrain on Earth, and of the extraordinary reward that patience eventually brought. The Ixigualasto Formation of northwestern Argentina occupies a stretch of high-altitude desert in San Juan province that is, in the frankest terms, deeply alien to the eye. The landscape is eroded into rounded formations of grey and pale lavender badlands, the soft sediment sculpted by wind and water into shapes that seem almost deliberate, almost architectural. Large spherical boulders of harder stone sit atop eroded pedestals, balanced improbably. Channels cut by intermittent floods expose layered sediments in cross-section, each layer a record of a different environmental moment from 230 million years ago. The place is called the Valley of the Moon, in Spanish, Valle de la Luna, and standing there, looking across that pale and silent landscape under the broad blue of an Argentine sky, the name feels entirely appropriate. The rocks of Ixigualasto were deposited during the late Triassic, in the Carnian and Nourian stages, when this part of what would become South America was a river basin draining toward the interior of Pangaea. Rivers flooded seasonally. Floodplains accumulated layer upon layer of fine sediment. Animals that died near the water's edge were sometimes buried quickly enough to preserve their bones. And so the Valley of the Moon became, entirely without intention, one of the great natural museums of the ancient world. Paleontologists began working there in earnest in the 1950s and 60s, and what they found transformed our understanding of dinosaur origins. The earliest excavations revealed bones of strange creatures unlike anything previously described from the Triassic of the Northern Hemisphere. Bones of animals that were clearly archosaurs, clearly members of the broad group that includes both dinosaurs and crocodilians, but that could not be easily assigned to any known category. Animals that seemed to stand at a crossroads, partway between the non-dinosaurian archosaurs and the true dinosaurs. Then, in 1963, the first truly extraordinary discovery came to light. A creature unlike anything anyone had previously seen, a small carnivore that immediately seemed to represent something close to the origin point of the entire dinosaur family tree. In the decades since, the bones have been studied from every angle, analysed with increasingly sophisticated techniques, compared with hundreds of other specimens from around the world. The animal has been named and renamed and debated, but its significance has only grown with time. Euraptor lunensis, the dawn thief of the Moon Valley. The name has an almost poetic quality that, for once, genuinely matches the significance of the creature it describes. Euraptor was small by dinosaur standards, perhaps a metre long, perhaps 4 or 5 kilograms in weight. It moved on 2 legs, with a long tail counterbalancing its slightly forward-leaning body. Its hands had 5 fingers, though the outer 2 were small and probably not functional for grasping. Its teeth were interesting, mixing the sharp recurved teeth of a carnivore with some flatter, less serrated teeth that suggested it may have eaten some plant material as well. This dietary flexibility, this omnivorous adaptability, is one of the features that made Euraptor so significant. It suggested that the very first dinosaurs were not specialists. They were opportunists, generalists, animals that would eat whatever presented itself. Euraptor lived approximately 231 million years ago, placing it right at the base of the Carnian stage of the late Triassic. It was not the only dinosaur in Ischigualasto. Moving through the same ancient river system at roughly the same time, hunting along the same floodplains and sheltering in the same sparse forests was a much more imposing animal. Herrerasaurus ischigualastensis, named for Victorino Herrera, the local goat farmer who first discovered its bones in 1959. Herrerasaurus was not small. At roughly 3 to 6 meters in length, depending on the individual, it was a genuinely significant predator, one of the largest carnivores in its ecosystem. Unlike Euraptor, there was nothing ambiguous about Herrerasaurus as a predator. Its jaws were long and lined with sharp recurved teeth designed for gripping struggling prey. Its hands bore large curved claws on the first 3 fingers, perfect for seizing and holding. Its neck was flexible and strong, and its hind limbs were long and built for speed, with the characteristically upright posture that defines the entire dinosaur lineage. Herrerasaurus has been the subject of enormous debate since its discovery. Some researchers have placed it at the very base of the dinosaur family tree, arguing that it represents a very early branch that split off before the main dinosaur lineages diverged. Others have argued it was a relatively derived theropod, a member of the great carnivorous dinosaur lineage that would eventually produce animals like Allosaurus and Tyrannosaurus. The debate is not fully settled, but what is not debated is its significance. Herrerasaurus was one of the earliest large dinosaurian predators known anywhere on Earth, and it lived in South America. Standing in that ancient Ischigualasto river basin, 231 million years ago, you would encounter these two animals in very different contexts. Euraptor would be quick and furtive, moving through the undergrowth or along the river's edge, pausing to investigate fallen logs for beetles, darting after small lizard-like reptiles, occasionally picking at a piece of carrion left behind by a larger predator. You might walk within 10 meters of one and not notice it until it moved. Herrerasaurus would be impossible to miss, moving across the open floodplain with the deliberate, unhurried confidence of an apex predator, its footprints pressing deep into the soft mud near the river's edge. If it noticed you, it would stop and assess you with large, forward-facing eyes. Those eyes tell us something important. Forward-facing eyes, eyes that provide overlapping visual fields and therefore good depth perception, are a predator's tool. Herrerasaurus was designed to judge distance, to calculate trajectories, to time a strike, in that still moment of mutual observation, you would feel, very clearly, that you were looking at an animal that had looked at prey animals before, and knew exactly what to do about them. But Herrerasaurus and Eoraptor were not alone in Isigualasto. They lived alongside a remarkable diversity of other animals, and understanding those other animals helps us understand the specific ecological position of these early dinosaurs. The Rauisuchians were still here, in this late Triassic world. Saurosuchus galilei, found in the same Isigualasto formation, was an enormous Rauisuchian, some estimates suggesting body lengths of 6 to 7 meters, making it one of the largest terrestrial predators of its time anywhere on Earth. With a massive skull armed with serrated teeth and a body supported by semi-erect pillar-like legs, Saurosuchus was a genuinely terrifying creature by any standard. It was clearly the apex predator of the Isigualasto ecosystem, larger and almost certainly more powerful than Herrerasaurus. This is a critical point that reshapes how we think about early dinosaur ecology. When we imagine early dinosaurs, we're often tempted to imagine them as already dominant, already impressive, already on their way to the world-ruling status they would eventually achieve. But in the late Triassic, dinosaurs were not at the top. They were part of a more complex food web in which multiple competing lineages occupied different predatory roles, and in which the largest and most powerful predators were not yet dinosaurs. Herrerasaurus was a significant predator, but it was probably not Saurosuchus's primary competition. And Eoraptor was not competing with either of them. They occupied different niches in the same ecosystem, different rungs on the same ecological ladder. And this stratified niche structure was, paradoxically, one of the things that allowed the early dinosaurs to survive and eventually expand when the great late Triassic extinctions began sweeping away the larger, more specialized animals. But let us linger a little longer in Isigualasto, because there are more animals to meet here, and they all contribute to our understanding of what the first chapter of the Jurassic Americas story looked like. Among the most fascinating of the Isigualasto dinosaurs is Pisanosaurus myrtii, described from only a single fragmentary specimen but important nonetheless. Pisanosaurus, if it is indeed a dinosaur and not a more basal archosaur as some researchers have argued, may represent one of the earliest ornithischians, one of the earliest members of the great herbivorous dinosaur group that would eventually produce the hadrosaurs, the ceratopsians, the stegosaurs, and the ankylosaurs of the Cretaceous. Even in this fragmentary form, even in this uncertain taxonomic position, Pisanosaurus hints at something important. The herbivorous dinosaurs, the great plant-eating lineages that would eventually become the most numerous and diverse of all dinosaurian groups, were also present at the very beginning. The dinosaur family tree was already branching at Isigualasto. And then there are the non-dinosaurian animals of this world, the creatures that give context to the dinosaur's ecological position. The Lagossuchids and other small pseudosuchian archosaurs that scurried through the undergrowth. The etosaurs, heavily armoured herbivores that fed on low-growing vegetation, their bodies encased in a mosaic of bony plates that would have clattered slightly as they moved. The strange, long-snouted Proterochampsids, crocodile-like reptiles that occupied semi-aquatic niches along the rivers. The Eoraptorans and their relatives moving through the transitional zones between forest and floodplain. Most interesting of all, perhaps, are the remains of what are clearly among the most advanced non-dinosaurian therapsids known from this time, the Odyssinodonts, and the advanced cynodonts that represent the mammal side of the archosaur-mammal split that had occurred hundreds of millions of years earlier. These creatures, small and furtive and almost certainly furry, moved through the same undergrowth as Eoraptor. They were, in a very real sense, our own distant relatives, watching the very earliest dinosaurs from the same ancient floodplains of what would become South America. Understanding Isigualasto means understanding that the story of the Americas, the story of the dinosaurs that would eventually fill this part of the world, began not in the grand, famous formations of the Jurassic Morrison beds or the spectacular outcrops of the Cretaceous Hell Creek Formation, but in a remote desert in Argentina, in rocks so old they are barely distinguishable from the raw material of the continental crust itself. It began with small animals moving carefully through an ancient world trying to survive, generation by generation, day by day, meal by meal. The descendants of those animals would eventually fill 2 continents. They would grow to sizes that stagger the imagination. They would adapt to conditions ranging from tropical coastlines to polar forests. They would become the defining creatures of an entire geological era. But all of that began here, in the Valley of the Moon, in the warm, wet mud of a late Triassic river plain. After Isigualasto, as we move forward in geological time toward the true Jurassic, we pass through another critical formation in South America, the Los Colorados Formation. Slightly younger than Isigualasto, the Los Colorados beds record a world already changing. Already dinosaur diversity is increasing. Already body sizes are growing. The earliest sauropodomorphs, the long-necked herbivorous dinosaurs that would eventually produce the great giants of the Jurassic, are making their appearance, and the ecological dominance of the Rauisuchians and other non-dinosaurian archosaurs is beginning to wane. What happened between the Isigualasto and Los Colorados worlds was a mass extinction event, or more precisely, a series of extinction pulses at the end of the Triassic period. Around 201 million years ago, something went badly wrong with Earth's climate again. More volcanism, associated this time with the Central Atlantic magmatic province, the enormous outpouring of lava that accompanied the very beginning of the breakup of Pangaea, pumped greenhouse gases into the atmosphere and triggered another period of global climate disruption. The Rauisuchians and Etosaurs and many of the other non-dinosaurian archosaurs that had dominated the Triassic world did not survive this transition. They went extinct or were reduced to tiny remnant populations that soon also vanished. And into those empty ecological spaces the dinosaurs expanded. Rapidly, impressively, the fossil record shows the change. Before the end Triassic extinction, dinosaurs were a minor component of most ecosystems. After it, they were becoming dominant. The great ecological radiation of the Jurassic dinosaurs was beginning. And now we need to understand the great geographic transformation that made the Jurassic Americas what they were. We need to talk about the breaking apart of Pangaea and the birth of two separate continents that would each develop their own unique dinosaur faunas, connected and yet increasingly distinct for the next 150 million years. There is a sound that the Earth makes when it tears itself apart, and it is not the sound you might expect. It is not a crack or an explosion. It is something slower and deeper, and in a strange way more frightening than those things. It is the sound of rock under tension, deep groanings from kilometers underground, the slow creak and shudder of continental crust being pulled in two different directions at once by the inexorable forces of mantle convection. It is a sound so low that most animals cannot hear it directly, though they may feel it as vibration, as occasional tremors, as the subtle, unsettling sense that the ground they stand on is not as solid as it appears. In the early Jurassic period, starting around 200 million years ago, and continuing for tens of millions of years afterward, the supercontinent Pangaea was doing exactly this. It was tearing itself apart. The mechanism behind this grand geological drama is plate tectonics, the movement of the great slabs of rock that make up Earth's outer shell, driven by the slow circulation of the hot mantle rock beneath. The mantle, that vast layer of rock between Earth's crust and its iron core, is not liquid in the way water is liquid, but it is plastic, capable of flowing over geological timescales under the enormous heat and pressure of Earth's interior. Hot material rises from depth, spreads laterally beneath the crust, drags the crustal plates along with it, and then sinks back down as it cools. This circulation, called mantle convection, is the engine that drives the slow dance of the continents. During the late Triassic and into the Jurassic, a great upwelling of hot mantle material beneath what is now the Central Atlantic region began to push the crust upward from below. The rock of the supercontinent, already under tension from the diverging mantle convection cells, began to fracture. Rift valleys formed, long narrow depressions where the crust had stretched and thinned. Initially these were continental rifts, valleys that filled with freshwater lakes and river systems. But as the rifting continued, as the plates moved further apart, the thinning crust eventually sank below sea level, and seawater from the ancient Tethys Sea began to pour in from the east. For millions of years, the early Central Atlantic was a narrow, shallow, highly saline sea, something like a greatly enlarged version of the modern Red Sea. The evaporation rate in this new tropical seaway was so high that enormous deposits of salt accumulated on the seafloor, salt that geologists can still find today beneath the sediments of the modern Atlantic Ocean floor. These ancient salt deposits, formed in that adolescent Atlantic over 170 million years ago, are among the most dramatic examples of how different the world of the Jurassic Americas was from the world we know today. As the central Atlantic widened, the land on either side of it began to separate. What would become North America drifted gradually westward and somewhat northward. What would become South America, initially still connected to Africa, began its own slow journey westward. The full separation of South America from Africa would take much longer, not fully complete until the Cretaceous period, but the directional drift had begun. The Americas were, very slowly, becoming the Americas. This gradual separation had profound consequences for the living world. As long as North America remained connected to what would become Europe and Africa through the northern reaches of Pangaea, animals could move between these landmasses. Migration was possible. Faunal exchange could occur. Species from one part of the ancient supercontinent could gradually expand their range to include other parts. But as the rifts widened and the seas deepened, these connections were severed, one by one, over millions of years. The effect on dinosaur evolution was enormous. Before the breakup of Pangaea, the early Jurassic dinosaurs of North America and South America were quite similar to each other, and to the dinosaurs of Europe and Africa. They were part of a single, interconnected world fauna. But as the connections broke, as the seaways widened and the distances between landmasses grew, the dinosaur faunas of different regions began to diverge. Populations that had once been part of a continuous species range became isolated. Over millions of generations, those isolated populations accumulated different mutations, faced different environmental pressures, adapted to different local conditions. They became different species. The one dinosaur world of the early Jurassic gradually became several somewhat different dinosaur worlds, each with its own distinctive cast of characters. But before that divergence fully set in, there was a period in the early to middle Jurassic when North and South America were still connected through a dry land corridor, or at least intermittently connected when sea levels were low enough to expose a land bridge. During this period, animals could move between the two regions, and the dinosaur faunas show evidence of this exchange in their similarities. Understanding this early connection, and then the later separation, is essential to understanding the full story of the Jurassic Americas. But let us not move too quickly through the process of rifting. The breaking apart of Pangaea was not only geologically dramatic, it was ecologically transformative on a scale that is difficult to fully appreciate from our modern perspective. Think about what it means for a continent to split. Think about what it means for land that has been continuous for hundreds of millions of years to begin separating. The rift zones themselves were landscapes of extraordinary dynamism. Volcanic activity was intense along the rift. As the crust stretched and thinned, magma found pathways to the surface and erupted. The lava flows that accompanied the central Atlantic magmatic province, estimated at some of the largest in Earth's history, covered enormous areas of what is now the eastern seaboard of North America, Brazil, and West Africa, with thick accumulations of dark basalt rock. Some of these lava flows are still exposed today as distinctive diabase ridges in New Jersey and Connecticut, as the Palisades along the Hudson River, as the dramatic coastal cliffs of eastern Brazil. They are the geological scars of the world's birth. For the animals living near these rift zones, this was a profoundly unsettling time. The ground shook, lava flows destroyed habitats, volcanic gases fouled the air in the immediate vicinity of eruption sites. River systems were disrupted as lava dams formed and then were breached. The local climate near active volcanoes was erratic, heated and then cooled, dried and then doused by volcanic rain. But farther from the active rifts, the effects were subtler and in some ways more consequential. The slow widening of the central Atlantic seaway changed the climate of the entire surrounding region. As an ocean widened, it brought moisture. The lands adjacent to the growing sea experienced higher rainfall than they had when surrounded by the dry interior of Pangaea. Vegetation spread, river systems expanded, habitats that had been marginal became productive, and animals followed the expanding green world. The early Jurassic saw a great radiation of herbivorous dinosaurs moving into previously inhospitable regions, as those regions became wetter and more vegetated. The sauropodomorphs, those long-necked, small-headed plant-eaters that had first appeared in the late Triassic, diversified rapidly in the early Jurassic, their body sizes increasing, their feeding strategies becoming more specialised. The rifting also created a new kind of environment that had not existed during the Pangean supercontinent phase: coastlines, specifically new eastern coastlines facing the growing central Atlantic and the new tidal zones, estuaries and coastal plains that came with them. These were rich environments, bathed in moisture, fed by nutrients washing down from the interior, warmed by the tropical sun. They became some of the most productive ecosystems of the early Jurassic Americas, and the fossils found in rocks deposited in these environments give us some of our most complete pictures of early Jurassic life. Imagine standing on one of those early Jurassic coastlines, perhaps 190 million years ago, somewhere along what would become the Gulf Coast region of North America. The land behind you is still largely continental in character, covered with conifer forests and spreading fern meadows. But before you, the new sea glitters under a bright tropical sun. The waves that lap at this shore are small and gentle, the sea still shallow and warm, and the life here is extraordinary. The coastal waters teem with fish, an early Jurassic fish fauna that includes several groups familiar from the late Triassic, newly diversifying after the end-Triassic extinction. Sharks of several types cruise the warm shallows, early ray-finned fish dart through underwater forests of green algae, and in the deeper water beyond the surf zone, larger shapes move. Marine reptiles, ichthyosaurs, those sleek dolphin-like swimmers that had evolved from land reptiles during the Triassic and adapted so completely to the ocean that they could no longer come ashore, now fill the ecological role that dolphins and tuna fill in our own oceans. Their large eyes, some of them the largest known in any vertebrate, gave them excellent vision in the dimly lit depths. On the beach itself, and in the low scrub behind the shoreline, the land fauna is already shifting from the Triassic patterns. The great Rauisuchians are gone, the Etosaurs are gone. In their place, dinosaurs are increasingly dominant, and among them, some quite remarkable animals are beginning to appear. This is where we start to see the transition from the small, marginal dinosaurs of Isigualasto to the grander creatures that will eventually define the Jurassic Americas. And to follow that transition, we need to move forward in time to the Middle and Late Jurassic, and to one of the most celebrated geological formations in the entire history of paleontology. We need to go to the Morrison Formation of North America. There is a stretch of the American West that has given paleontology more than perhaps any other single geological unit on Earth. It is a formation of sedimentary rock called the Morrison Formation, and it extends across portions of Colorado, Utah, Wyoming, Montana, South Dakota, Nebraska, Kansas, Oklahoma, New Mexico, and Arizona. When you drive through the dramatic landscapes of the Colorado Plateau, when you see the red and cream and lavender bands of ancient sediment exposed in canyon walls, when you walk across the dry grasslands of Wyoming and notice the dark shapes of ancient bones weathering out of the hillsides, you are seeing the Morrison Formation. You are walking through one of the greatest dinosaur graveyards the world has ever known. The Morrison Formation was deposited during the late Jurassic period, roughly 150 to 145 million years ago. During this time, the region that is now the American Southwest and Rocky Mountain West was not the dry, elevated landscape it is today. It was a broad, low-lying plain, much closer to sea level than the modern Colorado Plateau, and it was a world of remarkable ecological richness. Rivers wound across this plain, fed by mountains to the west that caught moisture from the Pacific and released it as rain and snowmelt. Seasonal flooding spread enormous volumes of sediment across the lowlands, burying dead animals in the kind of fine-grained deposits that are ideal for preserving bones. And the animals that lived and died on those ancient floodplains were unlike anything before or since. The Morrison Formation is the home of the great North American Jurassic giants, the dinosaurs that defined the public imagination of what a dinosaur was for over a century of paleontological discovery. These are the animals that changed how we think about life on Earth. These are the sauropods. The sauropods were, in the simplest possible terms, the largest land animals that have ever lived. And when we say large, we are not speaking in the careful, qualified way that scientists often speak. We are speaking in a way that requires no qualification. The great sauropods of the Morrison Formation were genuinely, almost incomprehensibly enormous. Understanding how large they actually were requires us to set aside our modern reference points entirely and start fresh. Think about an elephant, specifically an African elephant, the largest land animal alive today. A large adult male African elephant stands about 4 meters at the shoulder and weighs somewhere between 5 and 7 tons. This is a genuinely impressive animal. It dwarfs a human being. It could overturn a car without noticeable effort. Seeing one in the wild in open terrain where its full scale is visible is a humbling experience. Now consider that even the smaller sauropods of the Morrison Formation dwarfed this elephant. Diplodocus carnegie, one of the most well-known and most completely preserved of all Morrison sauropods, was roughly 27 meters long, its famously elongated neck and equally famous whip-like tail each contributing significantly to that total length. Diplodocus did not weigh as much as you might expect given its length, because its long neck and tail were relatively light structures, but it was still a massive animal, weighing perhaps 15 to 20 tons, 2 to 4 times the weight of a large elephant. Brachiosaurus altithorax, another Morrison titan, was shorter in overall length but far more massive. Its front legs were longer than its back legs, giving it a giraffe-like forward tilt that allowed it to raise its neck to exceptional heights. Estimates of its maximum reach vary, but it could likely access vegetation at heights of 10 meters or more, roughly equivalent to the roof of a 3-story building. Its total mass has been estimated at somewhere between 30 and 56 tons, the upper end of that range representing one of the heaviest animals known to have ever walked on land. And then there is Supersaurus, known from specimens discovered in Wyoming and Colorado, one of the longest animals ever to have walked the earth. Some estimates place Supersaurus at over 30 meters in total length, a creature so elongated that if it stood in a modern city street it would span nearly the width of an entire city block. But the sauropods of the Morrison were not simply about raw size. Their bodies were evolutionary masterpieces, engineered solutions to the problem of how to be extremely large and still function as a living animal. The skeleton of a large sauropod was not simply a scaled-up version of a smaller animal's skeleton. It was architecturally transformed. The vertebrae of the neck and back were hollowed out by large air spaces, reducing their weight while maintaining structural strength. This pneumatization, as paleontologists call it, was derived from a respiratory system that included large air sacs connected to the lungs, a system similar to that seen in modern birds and one of the features that dinosaurs and birds share as part of their evolutionary heritage. The neck itself is perhaps the most remarkable feature of a sauropod, and the one that raises the most biological questions. In Diplodocus, the neck contained 15 elongated vertebrae and could reach lengths of 6 or 7 meters. In Brachiosaurus, the neck was shorter but held more vertically. In Mamenchisaurus, a closely related but slightly different sauropod known primarily from China, the neck made up over half the animal's total length. What were these extraordinary necks for? The answer, perhaps surprisingly, is still debated by paleontologists. The most intuitive explanation, that long necks allowed sauropods to feed from treetops that shorter animals could not reach, certainly seems plausible for Brachiosaurus with its upward-reaching stance, but for Diplodocus, which seems to have held its neck more horizontally, reaching upward may have been biomechanically difficult. Some researchers have proposed that Diplodocus used its horizontal neck to sweep vegetation from a wide area at a single body position, like a very long-necked lawnmower, feeding efficiently on low-growing ferns and horsetails without having to move its enormous body more than necessary. Others have proposed social or sexual display functions for neck length. The debate is unresolved, which is one of the things that makes sauropod biology so endlessly fascinating. Standing at the edge of a Morrison Formation floodplain 150 million years ago, watching a herd of Diplodocus moving through the landscape, the first thing you would notice is the sound. These were not silent animals. Large herbivores moving through vegetation, their footsteps pressing deep into soft floodplain mud, would have generated a constant background of noise, the thud of enormous feet, each step sending a subtle vibration through the ground, the crack and tear of vegetation being stripped from stems, the deep, low vocalizations perhaps of animals communicating across distances, sounds below our hearing range or only just within it, felt as much as heard. The second thing you would notice is the scale. Even knowing the numbers, the measurements, the fossil records, nothing fully prepares the imagination for what a living Diplodocus would actually look like. The neck alone, sweeping gently from side to side as the animal walked, is longer than most buses. The body is the size of a small house. The tail, when flicked with any force, moves with a mechanical energy that produces a supersonic crack, the same physics that makes a bullwhip crack, though scaled up enormously. The ground trembles slightly with each step, not dramatically, not in the Hollywood earthquake fashion, but perceptibly. A low, rhythmic pulse in the earth beneath your feet. And they would not be alone. The Morrison sauropods were likely herding animals, or at least seasonally gregarious. Multiple species occupying the same landscape at the same time, partitioning the available vegetation between them by reaching different heights, feeding on different plant species, focusing on different habitats within the broader landscape mosaic. Diplodocus and Apatosaurus feeding on low to mid-height vegetation, Brachiosaurus reaching higher into the canopies of the tall conifers, Camarasaurus, slightly more robustly built than the long-necked specialists, perhaps feeding on tougher, more resistant vegetation that the others passed by. This was an ecological community of extraordinary complexity, and understanding it means understanding the plants as well as the animals. The Morrison Formation vegetation was quite different from any modern ecosystem. There were no grasses, no flowering plants, no fruits. The ground-level vegetation consisted mainly of ferns and horsetails, with cycads and cycadioids forming a medium-height shrub layer. The taller element of the vegetation was dominated by conifers, including relatives of modern Araucaria trees, dawn redwoods, and other primitive conifer groups. These trees could grow quite large, and their trunks and root systems are preserved in some Morrison Formation fossil beds, giving us a picture of ancient forest with canopy heights of perhaps 20 to 30 metres in the most productive zones near rivers. All this vegetation was fuel for the sauropod herds, and the sauropod herds were fuel for the great Morrison predators. Let us slow down for a moment, because the world of the Morrison Formation deserves more than a catalogue of giants. It deserves attention to its texture, to its daily rhythms, to the small details that accumulated into the full experience of what it was to be alive in that ancient landscape. There is a tendency, when talking about Jurassic dinosaurs, to focus on the superlatives, on the largest, the longest, the most dramatic. But the superlatives exist within a context, and that context, the ecology, the climate, the plants, the seasons, the insects, the smaller animals, is at least as interesting and ultimately as important to our understanding as the giants themselves. The Morrison Formation environment was not a single, uniform landscape. It was a mosaic of different habitats, each with its own characteristic plant and animal communities, all existing within the broader framework of a semi-arid to seasonally wet floodplain system in the interior of what was becoming North America. The primary driver of the Morrison environment was seasonality. This was not an equatorial rainforest climate, bathed in year-round moisture and maintaining a constant lush green through all seasons. It was a climate with a distinct wet season and a distinct dry season, and the contrast between these two seasonal extremes shaped every aspect of life in this ancient landscape. During the wet season, which likely lasted from a few months to perhaps half the year, the river systems of the Morrison were full and spreading. The rivers themselves were not small. They were continental-scale systems, fed by rainfall from the mountains to the west and draining eastward across the broad interior plain toward the shallow interior seas that periodically occupied parts of central North America. When they flooded, as they did regularly, they spread enormous volumes of water across the flat plain, creating temporary shallow lakes and swamps that could extend for dozens of kilometres on either side of the main channel. These flood events deposited the fine silt and clay layers that now make up much of the Morrison Formation, and they were the primary mechanism by which dinosaur bones were buried and preserved. During these wet season floods, the Morrison landscape was genuinely lush. Ferns and horsetails exploded in growth along the flood margins, covering the fresh sediment with dense green mats within days of floodwaters receding. Aquatic plants colonized the shallow temporary lakes. The rivers themselves teemed with fish. Crocodilians of several species patrolled the riverbanks and the lake shores, and the great sauropod herds moved through this transformed landscape, wading through shallow water, pulling vegetation from the now flooded fern meadows, following the advancing edge of the flood as it created new feeding opportunities. The dry season was different. When the rains failed and the rivers shrank back toward their channels, the Morrison landscape became a more challenging place. The temporary lakes evaporated, leaving behind pale expanses of cracked and dried mud. The ferns and horsetails that had covered the floodplains browned and died back. The rivers themselves shrank to their low-water channels, and in the worst drought years, even some of the smaller tributaries may have dried up entirely. The living world contracted around the remaining water sources. For large animals, this seasonal water stress was a significant challenge. The great sauropods had water requirements that are difficult to even estimate, given that we have no direct comparison animals in the modern world, but they were clearly enormous. An animal weighing 30 tons, active in warm to hot temperatures, with the metabolic demands of growth and reproduction, requires a very large volume of water on a daily basis. During the dry season, following the rivers toward their remaining water sources would have been a fundamental behavioral imperative. This seasonal movement following water and food across the landscape may explain some of the most remarkable features of the Morrison Formation fossil record. Bone beds, accumulations of the bones of many individuals of the same or different species, sometimes in extraordinary concentration, are known from several Morrison sites. At least some of these bone beds appear to represent mass death events associated with drought, perhaps groups of animals that converged on a drying water source and died when it gave out entirely. The bones of dozens of individuals, sometimes of different species, mixed together in a single geological horizon, speak eloquently of the hard seasons of the Morrison world. The soil itself in the Morrison environment tells us important things about the climate. Paleosols, ancient soils preserved in the rock record, show features that indicate seasonally wet and dry conditions. In the wet season soils, we see the features of waterlogged environments, root traces going deep into saturated sediment, the chemical signatures of iron reduction in oxygen-poor conditions. In the dry season soils, we see mud cracks, the chemical signatures of iron oxidation in well-aerated conditions, the root traces of drought-tolerant plants penetrating deep in search of moisture. The Morrison also preserves evidence of fire. Charcoal, fossilized as carbon particles in the rock, occurs at multiple Morrison sites, indicating that fires moved through the landscape during dry seasons. These fires, perhaps ignited by lightning during early season storms before the rains had fully set in, would have changed the landscape dramatically. Burning through this dry season fern and cycad ground cover, opening up patches of bare soil, and then, when the rains returned, creating a flush of new growth on the fire-cleared areas that would have been intensely productive for grazing animals. Fire ecology, that dynamic relationship between burn, regrowth, and grazing that characterizes many modern semi-arid landscapes, was already operating in the Jurassic Americas. The rivers of the Morrison carried more than water and sediment. They carried the bones of animals that had died upstream. Morrison Formation fossil sites along ancient river channels often preserve a mixed assemblage of animals that came from different habitats, their remains swept together by floodwaters and deposited in the same location. This mixing, which can make it difficult for paleontologists to reconstruct the precise ecological community of a specific site, is also one of the features that makes the Morrison so extraordinarily rich in fossils. The rivers were, in effect, a natural bone collection system, concentrating and preserving the remains of animals from across a vast landscape into specific geological horizons. The plants of the Morrison, while lacking the flowering diversity of a modern forest, were not without their own complexity. The conifers in particular formed genuine forest communities, with multiple species occupying different ecological niches, from the tall emergent trees of well-watered river valleys to the shorter, more widely spaced trees of the drier upland areas. Among the most common Morrison conifers were members of the Araucariaceae family, relatives of modern Araucaria trees including the monkey puzzle tree and the Norfolk Island pine. These ancient Araucarias could grow to impressive heights, their layered, tiered branch structure creating a distinctive forest silhouette that would be strangely familiar to a modern naturalist but also subtly wrong, like something seen in a dream. Cicadioids, or Bennettitals, were another dominant element of the Morrison vegetation. These plants, which superficially resembled cycads but were actually a separate and entirely extinct group, had thick barrel-shaped trunks covered with the scars of shed fronds and crowns of large, stiff, pinnately divided leaves. Some cicadioids bore reproductive structures that may have been among the earliest flower-like structures in plant evolution, potentially attractive to insects and very early pollinators, though true insect pollination as we understand it was still evolving during the Jurassic. The forest floor beneath these trees was a complex environment. Thick accumulations of fallen needles and fronds created a deep, spongy layer that retained moisture and insulated the soil from temperature extremes. Fungi played an enormous role in decomposing this organic material, breaking down the tough cellulose and lignin of fallen wood and returning nutrients to the soil. Some of these ancient wood-rotting fungi are preserved in the fossil record as traces in permineralized wood, their mycelia visible as fine threads in the wood's cellular structure. Insects were everywhere in the Morrison world, and they were enormously diverse. The Jurassic was a great period of insect diversification, and the Morrison captures a snapshot of that diversity in amber inclusions and body fossils preserved in fine-grained sediments. Beetles of many kinds were the most numerous, their tough exoskeletons making them more likely to be preserved than soft-bodied insects. Dragonflies with wingspans, sometimes exceeding modern species, cruised the riverbanks. Primitive moths and butterflies, their wings bearing very different patterns from their modern relatives, visited the cycadioid flowers. Cockroaches, one of the most ancient and conservative of all insect orders, scurried through the leaf litter in forms recognizably similar to their modern descendants. These insects were not merely background noise to the Jurassic ecosystem. They were essential players in the functioning of the entire ecological community. As decomposers, processing dead organic material, as pollinators, even in the primitive sense, as prey, providing food for a vast array of small vertebrates, and as competitors and parasites of the larger animals, something that is easy to forget when we think about ancient ecosystems, but that was as real in the Jurassic as it is today. In the rivers and lakes of the Morrison, a separate aquatic ecosystem operated in parallel with the terrestrial one. These ancient waterways were home to diverse fish communities, several genera of early freshwater sharks in addition to more familiar bony fish. Freshwater turtles of several species paddled through the shallows, their domed shells representing an early stage in the long evolution of a body plan that has proven so successful that it persists almost unchanged into the modern world. Frogs croaked from the shorelines during the wet season, their ancient calls echoing across floodplains that were otherwise dominated by the heavier sounds of large animals moving. And in the rivers themselves, patrolling the channels with the patient, unhurried confidence of expert ambush predators, were the Morrison crocodilians. Several genera of crocodile relatives inhabited the Morrison waterways, ranging from small, slender-snouted fish-eaters to larger, more robust forms capable of taking significantly sized prey. These were not quite the fully modern-looking crocodilians we're familiar with today, but they were close enough. The crocodilian body plan, which had been evolving since the Triassic, and which had experimented with terrestrial, swimming and even running forms during the intervening period, had by the Jurassic largely settled into the semi-aquatic ambush predator configuration that has proven so durable and successful. The Morrison crocodilians, like their modern counterparts, were primarily opportunists. They would take fish when fish were available. They would take small terrestrial vertebrates that came to the water's edge to drink. And in the deeper water, far from the banks, the largest individuals may have occasionally attempted ambushes on juvenile sauropods that ventured into the rivers to cool off or cross to the other bank. Whether this was a significant predatory strategy for the largest Morrison crocodilians is uncertain, but the possibility adds a dimension of danger to those ancient riverscapes that is easy to overlook. This, then, is the world of the Morrison Formation. Not a simple landscape of giants striding across an empty plain, but a complex, layered, seasonally dynamic ecosystem in which everything was connected to everything else. The sauropods needed the rivers and the vegetation. The vegetation needed the seasonal floods and the nutrients they carried. The floods shaped the landscape. The landscape shaped the animal communities. The animal communities, through their feeding and moving and dying, shaped the vegetation and the soils. And the insects and bacteria and fungi that no one talks about when they talk about Morrison Formation paleontology were as essential to this whole system as Brachiosaurus or Diplodocus. It was a complete world, a world that had been running for millions of years and would continue running for millions more. And into this lush, complex, ancient ecosystem, we now need to introduce the predators. Because the giants did not walk unchallenged across those ancient floodplains, something was always watching. A world with the largest herbivores in Earth's history needs predators of comparable ambition. This is not a moral statement or an observation about fairness. It is simply a consequence of ecology. Where there is abundant prey, predators evolve to take it. The question is not whether predators evolved alongside the great Morrison sauropods, but what those predators were like, how they hunted, and what the predator-prey relationship looked like in one of the most extreme ecological pairings in the history of life. The great predator of the Morrison Formation was Allosaurus fragilis, and few animals in the entire fossil record make quite the same immediate impression. Allosaurus was a large theropod, a bipedal carnivore of the great clade that would eventually produce Tyrannosaurus rex, though Allosaurus itself was not directly ancestral to Tyrannosaurus. It was instead a member of a different theropod branch, the Carnosaurs, and in terms of size and presence, it was the apex predator of the Morrison world. A large Allosaurus individual could reach lengths of 9 to 12 meters, with some exceptional specimens suggesting animals perhaps slightly larger. Its skull alone was enormous, nearly a meter long in large adults, though it was not the massive, bone-crushing skull of Tyrannosaurus. The skull of Allosaurus was instead a study in elegant engineering, lightly built for its size, with large openings in the bone called fenestrae that reduced weight while maintaining structural integrity. The jaws were lined with serrated teeth up to about 10 centimeters long, designed not for crushing but for slicing, for tearing through flesh in a manner that has been described as similar to an enormous pair of serrated scissors. The eyes of Allosaurus were large, and they were set in bony ridges, triangular crests above each orbit that may have served for display or for shading the eyes in bright sunlight. The overall face had an almost hawk-like quality, an impression of fierce, forward-focused intensity, of an animal whose entire morphology spoke of its relationship to prey. The forelegs were not the atrophied stumps they became in later tyrannosaurids, but were functional arms bearing 3 large curved claws, useful for gripping a struggling prey animal while the jaws did their work. Most Allosaurus specimens come from the Cleveland Lloyd Dinosaur Quarry in Utah and from Dinosaur National Monument on the Colorado-Utah border, and the abundance of Allosaurus material at these sites has been a source of both information and puzzlement to paleontologists for decades. At Cleveland Lloyd in particular, the bones of over 70 individual Allosaurus animals have been recovered from a single, relatively small fossil bed, making it the most concentrated accumulation of Allosaurus material known. Predators are usually rare in fossil assemblages, because there are always fewer predators than prey in any ecosystem. The extraordinary abundance of predators at Cleveland Lloyd has been interpreted as evidence of a predator trap, a patch of sticky mud, or a water source where prey animals became mired and died, attracting predators that then also became stuck. Or it may represent something about Allosaurus's social behavior, evidence of animals that gathered in groups at certain times of year. The question of Allosaurus's hunting behavior is one of the most fascinating in all of paleontology. Hunting behavior rarely fossilizes directly, and we must reconstruct it from anatomical evidence, from trace fossils including footprints and bite marks, and from comparison with modern animals. What we can say with some confidence is that Allosaurus had the anatomy of an active pursuit predator. Its legs were long and well muscled for running. Its center of mass was well positioned for rapid changes of direction. Its arms were powerful enough to grip, and its jaws were designed for rapid, repeated slicing bites, rather than the bone-crushing power bite of a Tyrannosaurus. Bite marks attributed to Allosaurus have been found on the bones of multiple Morrison sauropod genera, including Apatosaurus, Diplodocus, and Camarasaurus. These marks show that Allosaurus did indeed attack and eat sauropods. They do not, by themselves, tell us whether the sauropod was killed by Allosaurus or merely scavenged after dying by other means. But some bite marks appear on bones that would only have been accessible on a living animal, suggesting that at least some of the time, Allosaurus was actively hunting sauropods rather than merely cleaning up what had already died. The concept of a predator regularly hunting prey animals many times its own mass is not unprecedented in the modern world. Lions routinely take prey 3 to 4 times their own body weight. African wild dogs, hunting cooperatively, take prey disproportionately large relative to their individual size. Killer whales, the most formidable predators in the modern ocean, routinely attack prey that could crush them if the hunt went wrong. What these modern examples share is some combination of group hunting, specialized attack strategies, and a focus on vulnerable individuals such as juveniles, the elderly, or the injured. Some researchers have proposed that Allosaurus hunted using what they call a hatchet attack strategy. In this hypothesis, Allosaurus would open its jaws to an extraordinary degree, wider than the jaw opening angle of most other theropods, and then drive the upper jaw down into a prey animal with enormous force, using the skull as a weapon. The skull morphology of Allosaurus, with its relatively lightly constructed skull, designed to absorb stresses from the upper jaw, has been cited as anatomical support for this strategy. The attack would not be the crushing grip bite of a crocodile, but the impact-delivered wound of an enormous jawed hammer driving teeth deep into flesh. Whether this strategy was used against adult sauropods or primarily against smaller prey is uncertain. An adult Diplodocus, with its whip-like tail capable of delivering significant kinetic force, would not have been an entirely passive target. A Diplodocus that sensed a predator approaching could strike back with its tail, potentially breaking bones in a predator foolish enough to position itself incorrectly. The battle between the greatest carnivore and the greatest herbivore of the Morrison Formation was not one-sided, and both animals bore the marks of this ongoing relationship. Several Allosaurus specimens show healed injuries consistent with impacts from large animal tails or limb strikes. Allosaurus was not the only predator of the Morrison. Ceratosaurus nasicornis, another large theropod but from a completely different lineage, also occupied the predator role in the Morrison ecosystem. Ceratosaurus was smaller than the largest Allosaurus, and it bore a distinctive nasal horn and paired brow horns that made it visually immediately distinctive. The function of these horns is uncertain. They may have been used in intraspecific display, signaling fitness or dominance to other Ceratosaurus individuals. They may have had some role in hunting, or they may have been primarily decorative, the dinosaurian equivalent of the peacock's tail. Torvosaurus tanneri, known from both the Morrison Formation and from Cuival deposits in Portugal, was perhaps the largest predator in the Morrison ecosystem, with estimates suggesting some individuals reaching or exceeding 11 to 12 meters in length. Torvosaurus was a megalosauroid, a member of one of the oldest theropod lineages, and its massive, heavily built skull and robust arms gave it a somewhat different physical profile from the more lightly built Allosaurus. How these three large predators coexisted in the same ecosystem is an interesting ecological question. Modern large predator communities, such as those of the African savanna, show a pattern of niche partitioning in which different species focus on different prey types, different hunting habitats, or different times of activity. A similar pattern likely operated in the Morrison. Perhaps Allosaurus was the open country pursuit predator, running down prey on the broad floodplains. Perhaps Ceratosaurus was more closely associated with the riverine environments, spending more time in and around the water. Torvosaurus, with its heavier build, may have been a more ambush-oriented predator, relying on a single devastating rush from cover rather than extended pursuit. Among the smaller predators of the Morrison, one in particular deserves special attention. Ornitholestes hermanni was a small, agile theropod, perhaps 2 meters long, with long legs and a relatively large brain case suggesting good sensory processing. Its teeth were small, and its hands bore 3 functional fingers with modest claws. Ornitholestes was clearly not a sauropod hunter. Its prey was the small stuff, the lizards and small mammals and large insects that made up the lower tiers of the Morrison food web. But Ornitholestes is important because it represents a part of dinosaur diversity that is easy to overlook when the great giants dominate the story. The Morrison was not just an ecosystem of giants. It was a full ecological community, with small predators, medium predators, and large predators all occupying their appropriate niches. Among the non-predatory dinosaurs of the Morrison, the stegosaurs deserve particular attention. Stegosaurus stenops, the most famous member of this group, is one of the most visually distinctive dinosaurs in the fossil record, and the Morrison Formation is its primary home. The double row of large diamond-shaped plates running along Stegosaurus's back and the cluster of spikes at the end of its tail have been the source of scientific debate and public fascination since the first specimens were described in the 1870s. A full-grown Stegosaurus was a genuinely large animal, around 7 to 9 meters in length, and probably weighing somewhere between 2 and 4 tons, though its body was laterally compressed and relatively narrow, meaning its total bulk was perhaps less than its length might suggest. It moved on 4 legs, and its front legs were noticeably shorter than its back legs, giving it a characteristic low-headed posture as if it were permanently grazing close to the ground. The plates of Stegosaurus have been variously proposed as thermoregulatory devices, defensive weapons, and display structures. The thermoregulatory hypothesis, which suggested the plates functioned like radiators, absorbing or dissipating heat to help regulate the animal's body temperature, was popular for some time. But more recent work has suggested the plates were too thinly built and too poorly designed as heat exchangers to have been primarily thermoregulatory. The current consensus leans toward a display function. The plates were probably covered in life with a layer of skin containing blood vessels, making them potentially capable of flushing with colour, perhaps as a species recognition signal, or as a sexual display device, the dinosaurian equivalent of a peacock's train. The tail spikes, called a thagomizer in informal paleontological parlance, were clearly defensive weapons. The bones of at least one Allosaurus specimen preserve evidence of a healed wound, consistent with a Stegosaurus tail spike puncturing and then withdrawing from the vertebral bone of the predator. This extraordinary fossil provides a rare direct record of an actual encounter between predator and prey in the Morrison world. That day, approximately 150 million years ago, an Allosaurus attacked a Stegosaurus and lived to regret it. Both animals survived the encounter. Both animals carry its record in their bones. The herbivore diversity of the Morrison extended beyond sauropods and stegosaurs. The ornithopod dinosaurs, a group of primarily bipedal plant eaters that would later in the Cretaceous produce some of the most successful dinosaurs in Earth's history, were present in the Morrison in the form of Camptosaurus dispar. Camptosaurus was a medium-sized dinosaur, perhaps 5 to 7 meters long, that could move either bipedally or quadrupedally depending on context. When running, it moved on its hind legs. When feeding or moving slowly, it would drop to all fours and browse close to the ground. The diversity of the Morrison herbivores meant that different plant species and different feeding heights were exploited by different animals, creating a complex layered plant-eating community. Sauropods browsing at multiple heights from ground level to high canopy. Stegosaurus feeding on low-growing vegetation with its characteristically low head carriage. Camptosaurus browsing on medium-height plants, and perhaps rearing occasionally to reach higher vegetation. This dietary stratification allowed the entire herbivore community to coexist without competing directly for the same food resources, a principle called resource partitioning that operates in every modern diverse herbivore community, from the African savanna to the Amazon rainforest. The Morrison world was alive with this complexity, this layered interplay of species, each occupying its role in the web of life, each dependent on others, each in some measure shaping the others. It is easy to see the Morrison as a static picture, the way museum displays tend to present it, frozen specimens on pedestals under fluorescent lighting. But the Morrison was not static. It was dynamic, changing with the seasons, with the years, with the slow pulse of geological time. Animals moved, populations grew and contracted, drought years and wet years alternated, new sediment covered old landscapes. And to the south, in what was becoming South America, a parallel story was unfolding, a story with its own distinctive cast of characters, shaped by the increasingly separate evolutionary history of a landmass that was slowly drifting away from the rest of the world. If the Morrison Formation represents one chapter of the Jurassic Americas story, the South American Jurassic formations represent a different chapter, one that is in some ways even more extraordinary and that leads to consequences so remarkable that they are still being discovered and interpreted by paleontologists today. Because South America, drifting away from Africa and increasingly isolated from the northern landmasses, was developing its own unique dinosaur fauna, and some of the most surprising giants in the entire history of dinosaurs have their deepest roots in the ancient lands of South America. To understand the South American Jurassic, we need first to understand the geographic situation of that landmass during the Jurassic period. By the Middle Jurassic, roughly 160 to 170 million years ago, South America was in an interesting transitional phase. To its east, Africa was still connected to it along what would become the South Atlantic. That ocean was just beginning to open, its earliest floor sediments being laid down as the Great Rift that had begun in the Triassic continued its slow, inexorable expansion. To the north, the connection to what would become North America was tenuous, existing as a low-lying corridor that was periodically flooded by shallow seas and therefore not always available as a migration route. To the south and west, open oceans stretched to wherever the continental fragments that would eventually become Antarctica and Australia were drifting. This geographic semi-isolation had a fascinating effect on South American dinosaur evolution. Animals that crossed from the north or from Africa during times when corridors were available would arrive in South America, and then, when the corridors closed or the sea levels rose to block passage, be left to evolve in isolation. This isolation experiment, running over millions of years, produced an evolutionary trajectory for South American dinosaurs that was related to but distinct from the trajectories in the Northern Hemisphere. The late Triassic and early Jurassic of South America, as we have already discussed in relation to Ischigualasto, was the cradle of dinosaur evolution. But what happened after that initial radiation? What did South American dinosaurs do through the Middle and Late Jurassic as the northern landmasses were producing the Great Morrison fauna? The answer comes from a series of fossil formations scattered across the high-altitude Andean region and the Patagonian south of Argentina and Chile. The rocks here, laid down during Jurassic time in river basins and lake beds, preserve a fauna that shares some similarities with the northern Jurassic faunas, but also show significant differences. The sauropods were present here too, but evolving along somewhat different lines. The theropods were present, but again following a slightly divergent evolutionary path. Among the most fascinating of the South American Jurassic sauropods is the lineage that would eventually lead to the Titanosaurs, the group that in the Cretaceous would produce some of the largest animals ever to walk the Earth. During the Jurassic, the titanosauriform sauropods were already present in South America, and tracing their evolution through the rock record reveals a story of gradual experimentation with body size, neck length, and limb architecture that would eventually culminate in creatures of almost incomprehensible proportions. The titanosaurs belong to a broader group called the macronarians, characterized by a relatively robust skull and large nostril openings, in contrast to the more slender-skulled flagellocaudatan sauropods like Diplodocus that dominated the Morrison. This skull difference may reflect different feeding strategies. The macronarian skull may have been better adapted for processing tougher vegetation, using a more vertical, wider bite rather than the horizontal raking bite suggested for Diplodocus. In the Jurassic formations of Argentina, we find early macronarian sauropods whose anatomy already foreshadows what titanosaurs would become. The limb bones show the beginning of the broadening and thickening that would reach its extreme expression in the Great Cretaceous Titans. The vertebrae show the pneumatization, the airspace hollowing, that would allow later titanosaurs to maintain body integrity at enormous sizes without the skeleton becoming too heavy to support. This is evolution in progress, visible in the rocks, the gradual assembly of a body plan that would eventually break records. Alongside these ancestral titanosauriform sauropods, the South American Jurassic formations preserve theropod dinosaurs of considerable interest. The abelisaurids, a theropod group that would become the dominant large predators of the southern land masses in the Cretaceous, have their roots somewhere in the Jurassic of South America or Africa. While complete Jurassic abelisaurids are rare, fragmentary evidence suggests this lineage was already diverging from the ceratosaurian stock during the Jurassic. The abelisaurids would eventually develop a distinctive body plan characterized by short, often highly ornamented skulls, tiny forelimbs even more reduced than those of Tyrannosaurus, and powerful hind limbs. They were the tyrants of the southern world, filling the same ecological role in South America and Africa and India that Tyrannosaurus would fill in North America and Tarbosaurus in Asia. The South American Jurassic also preserves evidence of the earliest development of the ceratosaur lineage, a theropod group that produced some remarkable forms across the Mesozoic. Ceratosaurs, identified by distinctive features of the ankle bones and other skeletal elements, were present in both the northern and southern landmasses of the Jurassic world, representing one of the last widespread dinosaur groups before the growing separation of the continents made faunal exchange increasingly difficult. The landscapes these animals lived in across Jurassic South America were shaped by the same broad forces operating everywhere on the planet during this period. The climate was warm, generally warmer than today across all latitudes, because the extreme greenhouse conditions initiated during the Triassic had not fully abated. There were no polar ice caps. High-latitude regions that are today frozen tundra were in the Jurassic temperate or even subtropical forests. This global warmth meant that the latitudinal gradient in temperature was shallower than it is today, and that tropical and subtropical conditions extended much further from the equator. In South America, this warm climate, combined with the moisture brought by the easterly winds from the still narrow South Atlantic, produced lush vegetation across large parts of the continent. The Andes did not yet exist, or rather existed only as a very different, much lower mountain range, and would not reach their current dramatic heights until the Cenozoic. Without the high Andes to create a rain shadow, the interior of South America received more moisture in the Jurassic than it does in some regions today, supporting forests and river systems across what is now relatively dry Patagonia. These Jurassic Patagonian forests were dominated by the same conifer and cycad communities that characterize Jurassic vegetation worldwide, with Araucaria relatives prominent as they still are in southern South America today. Modern Araucaria trees, the monkey puzzle trees of the Andes and the Parana pine of southern Brazil, are living relics of this ancient Jurassic vegetation, and seeing them today in their native habitat gives some feeling of what Jurassic forests must have looked like, though of course the ancient forests were more extensive and the animals moving beneath their canopies were rather more dramatic. Some of the most important South American Jurassic deposits are found in the Neuquén Basin of Patagonia, a broad geological basin that spans parts of the Argentine provinces of Neuquén, Rio Negro and Mendoza. The Neuquén Basin has been producing extraordinary dinosaur fossils for over a century, and it continues to produce new discoveries at a remarkable rate. The Jurassic portion of the Neuquén Basin sequence preserves a window into a world that was developing slightly independently from the Morrison world to the north, a world in which some evolutionary experiments were being run that would have consequences reaching all the way into the Cretaceous. One of the critical evolutionary developments taking place in Jurassic South America was the refinement of the sauropod body plan in the direction of extreme size. We have talked about the Great Morrison sauropods and their impressive proportions, but the South American Titanosauriform lineage was beginning, during the Jurassic, the evolutionary journey toward body sizes that would eventually exceed even the Morrison giants. The full expression of this trend would not come until the Cretaceous, when Argentina would produce animals like Patagotitan majorum, currently the heaviest dinosaur known, estimated at between 60 and 77 tons, dwarfing even the largest Morrison sauropods. But the Jurassic was where the blueprint was drawn. Why did South American sauropods tend towards such extreme sizes? This is a question without a fully satisfying answer, but several factors have been proposed. The absence of certain competing herbivore groups in South America may have left ecological space for sauropods to expand without the competition that constrained their diversification in the north. The vegetation available in South America, perhaps different in nutritional content or physical characteristics from northern vegetation, may have favoured large body size for processing tough plant material. Or the isolation of South America may simply have allowed a particular evolutionary trend toward large body size to run further than it did elsewhere, unchecked by the mixing of faunas that occurred in the more connected northern landmasses. Whatever the reasons, the Titanosauriform evolutionary trajectory that began in the Jurassic of South America represents one of the great evolutionary stories of the Mesozoic. It is a story about the limits of what a land animal can be, about the engineering solutions evolution finds to the problem of moving a body of dozens of tons across the landscape, about the ecological consequences of having animals so large that almost nothing can threaten them. And while that story was developing on the land of South America, another story was developing in the waters that were increasingly surrounding and separating these ancient continents. In the growing seas of the Jurassic Americas, extraordinary creatures were evolving, creatures that command as much wonder as the land giants, and that reveal yet another dimension of the richness of this ancient world. There is a perspective on the Jurassic Americas that we have not yet taken, and it is perhaps the most dramatic perspective of all. It is the view from the water. Because the Jurassic period was not just a story of land, it was a story of growing oceans, of widening seaways, of marine ecosystems developing in the new water spaces created by the breakup of Pangaea. And in those growing seas, in the warm, shallow tropical waters of what would become the Gulf of Mexico and the Caribbean, in the slightly cooler waters of the early South Atlantic, and in the deep open ocean of the Panthalassic beyond, some of the most extraordinary animals in the history of life were swimming. Let us begin with the seaways themselves, because understanding the geography of the Jurassic marine world is essential to understanding the creatures that lived in it. By the Middle and Late Jurassic, the breakup of Pangaea had created a complex geography of land and sea in the Americas region. The growing Central Atlantic spread northward along the axis that separated North America from what was becoming northwestern Africa and southwestern Europe. This was a relatively narrow seaway in the Middle Jurassic, probably warm and highly saline, bathed in tropical sunlight, its shallow margins supporting some of the first reef-building communities to recover after the End-Triassic disruption. To the east, what would become the South Atlantic was beginning its opening, still narrow in the early Jurassic and only widening slowly through the period. Between North and South America, in the region that would eventually become the Gulf of Mexico, shallow continental seas were flooding the low-lying terrain of the connecting corridor, creating a warm, shallow epicontinental sea that would persist in various forms through most of the remainder of the Mesozoic. These shallow epicontinental seas, the Sundance Sea to the north and the various Gulf Coast and Caribbean embayments to the south, were enormously productive marine environments, their shallow depths warmed to the bottom by tropical sunlight, their nutrients replenished by rivers draining the adjacent continents. To the west of the Americas, the Great Panthalassic Ocean, that world-spanning body of water that had surrounded Pangaea since the beginning of complex life, continued to exist, though it was gradually being reduced as the Atlantic grew. The Panthalassic was deep, ancient, and home to its own extraordinary marine fauna, separate in some ways from the fauna developing in the new Atlantic seaways. The dominant large marine animals of the Jurassic seas were reptiles, and their dominance was as complete in the ocean as dinosaurian dominance was on land. The ichthyosaurs, those perfectly streamlined dolphin-like swimmers that had first evolved in the Triassic, reached their maximum diversity and abundance during the Jurassic. In the warm, shallow seas of what would become the Americas, ichthyosaur fossils are found at sites that allow us to reconstruct these animals in extraordinary detail. Ophthalmosaurus isenicus, one of the most completely known of all Jurassic ichthyosaurs, is a creature of breathtaking biological elegance. Its body was shaped like a large, perfectly streamlined projectile, with a crescent-shaped tail fin oriented vertically like a shark's tail, driving it through the water with a side-to-side oscillation. Its limbs had been transformed during millions of years of aquatic evolution into short, stiff flippers, their internal bones compressed and multiplied into a hypnotic mosaic of small bony discs that provided a rigid but flexible fin surface. And then there were the eyes. The eyes of Ophthalmosaurus were the largest, relative to body size, of any known vertebrate. In an adult animal of perhaps 4 to 6 meters in length, the eyes could be 23 centimeters in diameter, larger than a volleyball. These extraordinary eyes were held in shape by a ring of bones called sclerotic rings, which prevented them from collapsing under the pressure of deep dives, and deep dives are what those eyes were for, the combination of large eye diameter, allowing more light to reach the retina, and the structural support against pressure collapse suggests that Ophthalmosaurus was a regular deep diver, hunting in the dark water below the photic zone where sunlight does not penetrate. What was Ophthalmosaurus hunting in those depths? Almost certainly fish, and probably also the belemnites and ammonites that were extraordinarily abundant in Jurassic seas. Belemnites were squid-like cephalopods, whose calcified internal shells, called guards, are among the most common fossils in Jurassic marine sediments. They were clearly a major prey item for many Jurassic marine predators, and their hard guards have been found in the stomach contents of ichthyosaur specimens preserved with exceptional completeness. An Ophthalmosaurus diving into the darkness below 500 meters, its enormous eyes detecting the faint bioluminescent flashes of deep-sea prey, was an animal operating at the frontier of biological possibility for a reptile breathing air. Unlike dolphins, which are the obvious modern comparison for ichthyosaurs, these ancient marine reptiles gave birth to live young in the water, rather than coming ashore to lay eggs. We know this not from inference, but from direct fossil evidence. Multiple ichthyosaur specimens preserved in the process of giving birth have been found, the bones of partially emerged young visible within or beneath the skeleton of the adult female. The young emerge tail first, as in modern dolphins and whales, minimizing the risk of drowning during delivery. This extraordinary detail, this window into the reproductive biology of an animal that lived 160 million years ago, is one of the gifts that the fossil record occasionally offers, and it makes the ichthyosaurs feel not like abstract ancient creatures, but like real, warm-blooded nursing parents in a cold, dark sea. The plesiosaurs were the other great marine reptile dynasty of the Jurassic, and in many ways the more visually extraordinary of the two. Where ichthyosaurs had converged on a fish-like or dolphin-like body form, plesiosaurs had taken a completely different evolutionary path. They were built around a broad, flat body like a living raft, with two pairs of large paddle-shaped limbs projecting from the sides, and either a very long neck with a small head or a short neck with a very large head, depending on which of the two major plesiosaur groups they belonged to. The long-necked plesiosaurs, sometimes called elasmosaurids in their later Cretaceous forms, though the Jurassic representatives were somewhat different, were among the most visually striking animals in the history of life. Their necks could contain as many as 76 vertebrae, more than any other known vertebrate, creating a serpentine length of neck that could account for more than half the animal's total body length. These necks were not as flexible as they look in museum reconstructions. The vertebrae of plesiosaur necks were shaped in ways that restricted lateral bending, and the neck was probably held relatively straight in life, swept from side to side while the body remained more stationary, or angled downward to snap at fish below the swimming animal. In the Jurassic seas of what would become the Americas, several plesiosaur genera are known from fossil deposits in marine strata. Their remains tell of animals that patrolled the warm, shallow seas of the epicontinental seaways, feeding on the abundant fish and cephalopods of those productive waters. Imagine one of these animals at the surface, its small head and extraordinary neck curving out of the water for a moment as it breathes, the broad body visible just below the surface, the four great paddles moving in a slow, synchronized underwater flight. Then the head submerges, the neck straightens, and it descends into the warm green water to hunt. The short-necked, large-headed plesiosaurs, the pliosaurs, were a different kind of animal entirely. Where the long-necked forms were delicate-seeming, almost gentle in their proportions, the pliosaurs were built for power. Short necks, massive heads, enormous jaws lined with conical interlocking teeth. They were the apex predators of the open ocean, the largest of them capable of taking other marine reptiles as prey. The Jurassic Americas were home to several plesiosaur genera, and the fossils of some of them suggest animals of genuinely impressive size, the largest with skulls approaching 2 meters in length. The teeth of large pliosaurs were extraordinary structures. Long, conical, with circular cross-sections, they were designed not for slicing but for gripping and crushing. An animal seized in pliosaur jaws could not twist free. The interlocking of upper and lower teeth when the jaws closed created a cage of bone from which there was no escape. The bite force of a large pliosaur has been estimated in some studies at tens of thousands of newtons, among the highest of any known animal. In the open ocean of the Jurassic Americas, a large pliosaur was essentially invulnerable to predation. It was the apex of the marine food web, the final answer to every escalation in the predator-prey arms race that played out below the waves. The fish of the Jurassic seas were not passive bystanders in this world of marine giants. The Jurassic saw an important evolutionary transition in fish diversity, with the ray-finned fishes, the actinopterygians, diversifying rapidly and beginning to approach the dominance they hold in modern aquatic ecosystems. Several important ray-finned fish lineages made their appearance or underwent significant diversification in the Jurassic seas of the Americas region. Among them were early representatives of groups that would eventually give rise to modern teleost fishes, the extraordinarily diverse group that today includes everything from tuna to goldfish. The sharks of the Jurassic were also a diverse and important part of the marine ecosystem, though they were different in important ways from modern sharks. Several shark lineages that are now extinct were common in Jurassic seas, while the ancestors of some modern shark groups were also present, though as smaller and less derived forms than their modern descendants. Hybodont sharks, a group with a distinctive fin spine arrangement and more primitive dentition than modern sharks, were among the most common. They were medium-sized predators occupying a middle tier in the marine food web, feeding primarily on fish and cephalopods, themselves prey for the larger ichthyosaurs and pliosaurs. The ammonites deserve particular attention as we paint this picture of the Jurassic seas of the Americas, because they were in many ways the most characteristic animals of the Mesozoic ocean. These shelled cephalopods, relatives of modern nautiluses but far more diverse, filled the Jurassic seas with their coiled and sometimes bizarrely modified shells in bewildering variety. Hundreds of ammonite genera are known from Jurassic deposits worldwide, each species identifiable by the distinctive pattern of the suture lines where the internal walls of the shell met the outer whorl, patterns that range from the nearly simple to the extraordinarily complex. Ammonites were active swimmers, probably moving through the water column by jet propulsion like modern cephalopods, their tentacles trailing to seize small prey items. They lived in the outermost chamber of their spiral shell, the older chambers behind them sealed by dividing walls and filled with gas to provide buoyancy, an elegant solution to the engineering problem of neutral buoyancy in an active, mobile marine animal. Their shells, beautifully preserved in countless Jurassic marine formations across the Americas, give us one of our most precise tools for dating ancient marine deposits. Because ammonite species evolved rapidly and had wide geographic distributions, the presence of specific ammonite species in a rock layer allows geologists to date that layer with extraordinary precision by comparison with the worldwide ammonite record. And so the seas of the Jurassic Americas were full of life in every depth zone. Plankton at the surface converting sunlight to organic matter, forming the base of the entire food web. Filter-feeding invertebrates just below the surface, straining the plankton from the water. Small fish and cephalopods above the seafloor, darting through a three-dimensional world of predator and prey. Larger fish and ichthyosaurs in the open water, cruising steadily in search of concentrations of prey. Pliosaurs patrolling the margins of the deep water, their enormous presence felt by every other animal in their vicinity. And on the seafloor, a community of bivalves, gastropods, sea urchins, brittle stars, and other invertebrates processing the organic matter that rained down from above. This was the world beneath the waves of the Jurassic Americas, as extraordinary as the world above the waves, and in some ways more alien, more distant from our everyday experience. But equally real, equally complex, equally worthy of our attention and our wonder. Nothing in the history of Earth is permanent. We have said this before in the course of this story, and we will say it again, because it bears repeating. The Great Morrison world, that magnificent ecosystem of giants and ancient forests and shallow inland seas, was not an endpoint, it was a chapter. And like all chapters, it had an ending. Around 145 million years ago, the Jurassic Period gave way to the Cretaceous, and although this boundary in geological time is defined by changes in the fossil record and the rock record rather than by any single dramatic event, the world that existed after it was meaningfully different from the world that existed before. The transition was not instantaneous. The changes that defined it accumulated over millions of years, overlapping and interacting in complex ways. But the cumulative effect of those changes was a transformation of the Americas that would ultimately set the stage for the final act of the dinosaur story. Understanding how the Jurassic ended in the Americas requires understanding the broader geological changes that were reshaping the world during this period. The most important of these was the continued fragmentation of Pangaea. By the late Jurassic, the supercontinent was no longer a single landmass in any meaningful sense. The central Atlantic had grown from a narrow seaway to a genuine, if still relatively young, ocean. South America was continuing its slow drift westward and southward, its connection to Africa growing more tenuous as the South Atlantic widened. North America was separating from Europe along the line that would eventually become the North Atlantic. These separations had profound implications for the climate of the Americas. As ocean circulation patterns changed, as new oceanic seaways opened and allowed the mixing of waters that had previously been isolated, the thermal properties of the global ocean shifted. Ocean currents that had been redirected by the presence of land bridges or shallow seaways were rerouted. Water temperatures changed. The distribution of warm and cold water across the globe was reconfigured. In the late Jurassic and earliest Cretaceous, the climate of North America was changing. The semi-arid to seasonally wet conditions that had prevailed during the Morrison period were giving way to something different. Evidence in the rock record suggests that the late Jurassic saw increasing aridity in parts of western North America, with the red beds and evaporate deposits that characterize desert conditions becoming more prominent in some regions. The inland seas that had periodically flooded the continental interior during the Morrison period retreated, and the landscape became drier and more varied. For the great Morrison sauropods, these changes were consequential. The broad floodplains that had provided such rich feeding grounds for the giant herbivores began to shift in character. The river systems that had watered those plains changed in their patterns and extent. The vegetation that had supported the enormous biomass of sauropods and other herbivores was reorganized. Some areas that had been productive became less so. Others changed in their plant communities in ways that may have affected the feeding strategies of the dinosaurs that depended on them. The late Jurassic also saw changes in the dinosaur fauna itself. Some of the classic Morrison genera, the great sauropods and the large theropods that shared their world, persisted into the earliest Cretaceous in some regions, but others seem to have declined or disappeared from parts of their former range near the Jurassic-Cretaceous boundary. The composition of dinosaur communities was shifting. New groups were diversifying to fill niches that were changing as the vegetation and climate changed. This is also the period when North America began losing its direct overland connection to Europe, which had existed through the northern part of Pangaea throughout much of the Triassic and early to Middle Jurassic. As the North Atlantic opened and widened, the faunal exchange that had made the dinosaurs of North America and Europe similar in many respects became progressively more difficult. The dinosaur faunas of the two regions began to diverge more significantly, each following its own evolutionary trajectory as the populations were cut off from one another. To the south, South America was beginning a long period of partial isolation that would have enormous consequences for the evolution of its dinosaur fauna. As the South Atlantic opened and Africa drifted away, South America became increasingly an island continent, or more precisely a subcontinent with limited connections to the north through the Central American region. This isolation would ultimately lead to the extraordinary diversification of the Titanosaurian sauropods and the abellisaurid theropods that characterize the Cretaceous of South America, a fauna so distinctive that it stands apart from the dinosaur communities of the Northern Hemisphere. But these were future developments, unfolding over the long sweep of the Cretaceous period. In the final act of the Jurassic Americas story, we are looking at a world in transition, a world that is beautiful and remarkable in its own right, even as it is beginning to change into something new. Let's stand, one last time, in the late Jurassic landscape of what would become North America. We are somewhere on the broad floodplains of the Morrison Basin, in the last days of the Jurassic, perhaps 148 million years ago. The light is the warm amber light of late afternoon, angled low across the landscape, turning the dust in the air to gold. Before us, a river winds through a floodplain that is greener than it will be a few million years from now, fed by the reliable monsoons that still characterize the late Jurassic climate of this region. In the distance, a group of Diplodocus individuals is moving toward the river. There are perhaps 7 or 8 of them, adults and subadults, their long necks swaying with the slow rhythm of their walking. They are enormous and unhurried, and utterly at home in this landscape that has been their lineage's home for tens of millions of years. Their footsteps are visible in the soft ground near the river's edge, each print the size of a dining table, pressed deep into the mud by the weight of dozens of tons moving above. At the river's edge, a large stegosaurus is drinking, its small head dipped close to the water, the double row of plates along its back gleaming in the late light. It is aware of the approaching Diplodocus herd, but shows no concern. They are not competitors for the same food, and in the broad ecology of this landscape, herbivores of different feeding strategies are more companions than rivals. The Stegosaurus lifts its head, water running from its jaws, and looks across the river for a moment with a slow, ancient calm. Above the river, a pterosaur is fishing, quartering the surface with expert precision, occasionally dipping its long jaws to pluck a fish from just below the surface. Its wingspan is perhaps 3 meters, making it one of the medium-sized species, not yet approaching the giants that will evolve in the Cretaceous. It is perfectly at home in the air, its movements economical and graceful, its large eyes tracking the movement of fish shadows in the clear shallows. And in the shadow of a fallen Araucaria trunk where the wood has been softened by fungi and turned to a spongy dark matter that beetles tunnel through, a small creature is moving through the leaf litter. It is perhaps 15 centimeters long. It has fur, fine and soft, probably light brown or grey, and large dark eyes adapted for night vision. Its teeth are small and sharp, designed for insects, and perhaps the occasional small vertebrate. It is a mammal, or very close to one, and it is going about its business with the quiet diligence of a creature that has learned to survive by being invisible. This small furry animal moving through the shadow while the great dinosaurs drink and feed and move across the landscape is our ancestor. Distant, unrecognizable, utterly different from us in almost every way, but carrying within its genome the seeds of everything that we would eventually become. The large brain, the complex social behavior, the capacity for learning and adaptation, all of that is latent, unrealized, waiting for 66 million years and an asteroid and a mass extinction to give it room to grow. But that is not the story we're telling tonight. Tonight we're here in the Jurassic. Tonight we're here in the warm late light and the smell of river water and ancient mud and the distant sounds of the greatest animals that ever walked the earth. Tonight we are here in the Americas before they were the Americas, in a world so ancient and so beautiful that it almost does not seem real. The Jurassic period lasted from 201 million years ago to 145 million years ago. 56 million years! That is more than twice the time that has elapsed since the extinction of the non-avian dinosaurs at the end of the Cretaceous. It is a span of time so vast that within it, ecosystems rose and fell, species evolved and went extinct, oceans opened and land bridges formed and were submerged. The Jurassic of the Americas was not one thing. It was many things, many worlds, each one succeeding the last in the slow rhythm of geological time. We have visited only a few moments from this vast span. We have stood in the Triassic river systems of Isigualasto and watched the first dinosaurs move through the world. We have followed the rifting of Pangaea and the birth of the Atlantic. We have walked through the forests of the Morrison Formation and looked up at animals so large that the mind struggles to hold them. We have looked out across the warm, shallow seas of the epicontinental seaways and seen the marine giants moving in the green water. We have visited the South American Jurassic and traced the beginnings of the Titanosaurian lineage that would eventually produce the largest land animals in Earth's history. And now we're standing at the end of the Jurassic watching the last great act of this particular chapter play out in the amber light of a late afternoon that is also, in a sense, a late era. The great dinosaurs of the Jurassic Americas will not disappear suddenly. They will fade slowly over millions of years, replaced by new lineages, new body plans, new ecological configurations. The Cretaceous will be a different world, in many ways a richer and more complex world, with more diverse vegetation and more diverse dinosaur faunas, and eventually, in its last days, the first flowering plants transforming the landscape with colour and scent. But the Jurassic has a quality that no other period quite captures. It is the middle chapter of the age of dinosaurs, the period when the world belonged to these creatures most completely, most purely, most inevitably. Before the complexities and contingencies of the Cretaceous, before the beginning of the end that the asteroid would eventually deliver. The Jurassic is the heart of the dinosaur story, and the Americas were at the heart of the Jurassic. The river is catching the last light now, turning from gold to copper to the deep rose of early dusk. The Diplodocus herd has reached the water and is drinking, their long necks curving down from their enormous heights, the water disappearing into those great bodies in long, slow pools. The Stegosaurus has moved downstream and is feeding on a patch of low fern growth, methodical and unhurried. The pterosaur has wheeled away over the tree line and disappeared into the gathering blue of the early evening sky. Somewhere in the deeper forest an Allosaurus is moving. We cannot see it from here, but we know it is there, as it has been there, hunting these floodplains and river corridors for thousands of generations, part of the great web of life and death that has been running in this place for longer than we can easily comprehend. It too belongs here. It too is part of this world that we are visiting on this quiet evening at the edge of the Jurassic. The small mammal in the leaf litter has paused. Something has registered on its extraordinarily sensitive nervous system, not the Allosaurus, which is too far away, but something else, a sound, a vibration, a change in the quality of the air. It holds perfectly still for a moment, its eyes wide, its whiskers quivering. Then, satisfied that the change is nothing threatening, it continues its patient exploration of the fallen log, its nose working constantly, its small, clever hands turning over fragments of bark to reveal the insects hiding beneath. It is going to be a long night in the Jurassic Americas. The stars, when they appear, will not be the stars we know. The constellations have not yet assumed their modern arrangements, the slow drift of the stars through the sky over geological time having moved them from positions we would not recognize. But the stars themselves are the same stars. The Milky Way arches overhead, vast and bright in the darkness far from any artificial light, a river of ancient light connecting the present to a past so deep it makes the Jurassic feel recent. The night sounds are beginning, insects of 100 species establishing their evening rhythms in the warm air, the distant sound of something large moving through water at the river's edge, the call of a small dinosaur, perhaps a juvenile from somewhere in the middle distance, and beneath all of it, the deep silence of the ancient world, the silence of a planet going about its business on a scale and at a pace that makes all of human history seem like a brief disturbance in a very long quiet. This is the Jurassic Americas. This is where the greatest land animals in Earth's history lived and died and left their bones in the rock for us to find millions of years later. This is where the story of two continents began, where the geological forces that would eventually shape everything from the Rocky Mountains to the Andes were just beginning their slow work. This is a world that is gone, utterly and irreversibly gone, and yet preserved for us in rock and in the light of scientific investigation, available to us still, across a gulf of time that staggers the imagination. Let us stay here a little longer in the last light of the Jurassic Americas. Let the sounds of this ancient world accompany you. Let the images of great creatures moving through ancient landscapes settle into your mind like the soft sediment settling at the bottom of an ancient river. Let the scale of this story, 150 million years of life and change and extraordinary creatures, let that scale work on your sense of time and proportion in the way that only the deep past can. The dinosaurs of the Jurassic Americas are gone, but the continents they walked on are still here, still drifting on the slow currents of the mantle, still carrying in their rocks the record of everything that happened upon them. The Rocky Mountains, which did not yet exist in the Jurassic, will one day erode to expose Morrison Formation rocks that have been buried for 150 million years, and in those rocks, the bones of animals that walked this ancient world will come to light again. Discovery by discovery, specimen by specimen, the story of the Jurassic Americas is still being assembled, still being told, still yielding new wonders to the patient people who search for them in the stone. And perhaps that is the most remarkable thing of all, that a world so remote, so ancient, so completely gone can nevertheless be recovered, that the careful reading of rocks and bones and ancient soils and chemical signatures can bring it back, not fully, not completely, but enough. Enough to stand here in the imagination and watch the last light of the Jurassic fall across a landscape of giants. Enough to feel, for a moment, the deep time of this planet, the incomprehensible scale of its history, the extraordinary richness of the life that has moved across its surface and through its waters in the long billions of years since the first living cell divided in an ancient sea. We are part of that story. Our atoms were forged in the cores of stars that died before our sun was born. Our evolutionary heritage runs back through every ancestor that ever survived in a world that was trying to kill it, all the way back to the first cells, to the first chemistry, to the beginning. We are the universe becoming aware of itself, looking back across geological time at the worlds that preceded us, finding in those ancient worlds both the humility that comes from understanding our place in deep time and the wonder that comes from knowing how extraordinary a place the universe has made of this small blue world. The Jurassic Americas are gone, but we are here, and we remember. There is a reason why the story of the Jurassic Americas matters beyond the simple fascination of ancient creatures and vanished worlds. It matters because it tells us something about the nature of change, about the nature of life, about the relationship between the physical planet and the living world that rides upon it. The Jurassic Americas were the product of a convergence of geological forces operating on timescales so vast they are difficult to grasp. The breakup of Pangaea, the opening of the Atlantic, the changes in ocean circulation and global climate that those tectonic events produced, the slow drift of continents through different latitudinal positions, changing their climatic regimes over millions of years. All of these geological processes, grinding away at speeds that make glacial slow seem rapid, were nevertheless the fundamental drivers of everything we have talked about tonight. Because without the breakup of Pangaea, there would have been no Americas. There would have been no separation of North and South American dinosaur faunas, no independent evolution of the titanosaurians in the south, no Morrison ecosystem in the north. The geographic and therefore ecological and therefore evolutionary distinctiveness of the Jurassic Americas was entirely a product of geology, of rocks moving. This is one of the great insights of modern Earth science, that the history of life cannot be understood separately from the history of the rocks that life lived on. Geology and biology are not separate stories. They are the same story told at different scales. The tectonic forces that moved continents were the stage on which evolution played out. The volcanic events that changed the atmosphere were the cues that altered the plot. The slow changes in sea level that connected and separated populations were the mechanism by which evolutionary divergence was triggered or interrupted. Understanding the Jurassic Americas means understanding this deep connection between the physical and the living. It means following the thread from mantle convection to plate movement, to continental separation, to climate change, to ecosystem change, to evolutionary change, to the specific animals we have been describing tonight. That thread is real. It connects magma in Earth's mantle to the specific shape of a brachiosaurus neck. It connects the chemistry of ancient seawater to the enormous eyes of an ophthalmosaurus. It connects the slow drift of a continent across the face of the planet to the emergence of a lineage of South American sauropods that would eventually be the largest land animals in Earth's history. There is also a message in this story about contingency, about the role of chance in the history of life. The dinosaurs that dominated the Jurassic Americas were not the inevitable product of evolution working toward a predetermined goal. They were the result of a specific series of historical accidents. If the end-Triassic extinction had not happened, the Rauisuchians might have survived and continued to dominate the large predator role, leaving less room for large theropod dinosaurs to diversify. If the breakup of Pangaea had happened differently, if the Central Atlantic had opened earlier or later, or along a different axis, the faunal exchange and isolation patterns that shaped the Jurassic faunas would have been different. If the Morrison Formation had been deposited in a different climate zone, the specific vegetation and water regime that supported those extraordinary sauropod communities would not have existed. Every species that has ever lived is a frozen accident, a snapshot of evolution caught in a specific environmental and historical context. The great Morrison sauropods were not an inevitability. They were a possibility that was realized, contingently, because of a specific convergence of geological, climatic, and evolutionary circumstances that will never be exactly repeated. This is both humbling and wonderful. It means that the history of life is genuinely creative, genuinely novel, genuinely open-ended. It means that the world of 150 million years ago was not just an older version of today, but a genuinely different realization of life's possibilities, no less valid and no less extraordinary for being gone. And it means that the world of 150 million years from now, if anything is alive to experience it, will be equally different from today, equally novel, equally full of creatures and ecosystems that we cannot predict or imagine from our current vantage point. The Jurassic Americas remind us that the world is not static. It is not finished. It is still becoming, still changing, still producing new configurations of land and sea and life that will look as alien to any future observer as the Morrison world looks to us. One of the things that studying ancient life does for us is to recalibrate our sense of time. We tend, inevitably, to think of the present as the culmination of history, as the point toward which everything was heading. But the fossil record tells a different story. The present is just the current moment in an ongoing process that began before the first cells divided and will continue long after the last human thought has faded. The Jurassic Americas were not a step toward us. They were complete in themselves, as we are complete in ourselves. Every moment in Earth's history was the full expression of what life could do with what it had in that moment. This is not a diminishment of our own time or our own existence. It is the opposite. Knowing that we inhabit a brief, contingent, unrepeatable moment in the 4 billion-year story of life on this planet makes the present more precious, not less. Every morning you wake up, you're waking up in a world that has 4 billion years of history behind it and an unknowable future ahead of it. The sunlight falling through your window has fallen through the atmospheres of countless different Earths over geological time, each one as real and as full of life as this one. The ground you walk on has been walked on by creatures that would be unrecognizable to us, and will be walked on by creatures that we cannot imagine. We are part of a story that is still being told, and the Jurassic Americas are one of the earlier chapters, a remarkable chapter, full of extraordinary events and extraordinary creatures, a chapter that shaped the world we live in, that set in motion evolutionary lineages whose consequences are still playing out, that left its mark on the rocks beneath our feet and in the anatomy of every bird that flies overhead, every crocodile that waits in its river, every mammal that nurses its young, every living thing on Earth today that can trace its ancestry back through deep time to a world of ancient giants and warm Jurassic seas. So when you see a bird perched on a branch, you are seeing a dinosaur, a descendant of the great theropods of the Jurassic, reduced in size, covered in feathers that are the refined descendants of the scales that covered Allosaurus, but a dinosaur nonetheless. The dinosaurs did not go extinct at the end of the Cretaceous, only the non-avian ones did. The birds are the dinosaurs' survivors, their continuing presence on this planet a living connection to the world we have been visiting tonight. And when you find yourself somewhere in nature, somewhere away from the noise and complexity of the modern human world, and the silence opens up around you, and you can hear the insects and the birds and the wind in the trees, and the distant sound of water, you are hearing, in a muted and transformed way, something like what the ancient world sounded like. Not the same, not even close, but made of the same materials, the same fundamental biological and physical processes, the same ancient relationship between life and land and water and air. The Jurassic Americas are very far away in time, but they are not as far away as they sometimes feel. They are part of the same story we are living in. They are part of what we are. And knowing that, feeling that, is one of the gifts that the deep past has to offer us. Before we close this journey through the Jurassic Americas, let us trace one more thread. Let us follow the legacy of this ancient world forward through time to see how the Jurassic Americas contributed to the world we live in today. Because the Jurassic Americas did not simply end and disappear. They left behind a legacy that is written in the rocks, in the living world, and in the very shape of the continents beneath our feet. The most obvious legacy is the rock itself. The Morrison Formation, that great Jurassic fossil bed that has given us so many extraordinary dinosaur specimens, is still there. It is exposed across hundreds of thousands of square kilometers of the American West, weathering out of canyon walls and badland hillsides, yielding new discoveries to paleontologists every year. The bones it contains have been in the ground for 150 million years, waiting with extraordinary patience to be found and studied and to tell their stories. Some of the most important discoveries in the entire history of paleontology have come from the Morrison Formation, and some of the most important discoveries have not yet been made. There are certainly species yet to be found in those ancient sediments, ecological relationships yet to be understood, behaviours yet to be reconstructed from bone and track and chemical signal. The Morrison is not a closed book. It is an ongoing conversation between the past and the present, a dialogue that has been running since the first fragments of dinosaur bone were extracted from those rocks in the 1870s. The South American Jurassic formations are even less completely known than the Morrison. Vast stretches of the Neuquén Basin and the other Jurassic Age deposits of Argentina and Chile remain only partially explored. New species are being described from South American Jurassic formations at a steady rate, and each new specimen adds nuance and detail to our picture of the early South American dinosaur fauna. The story of South American Jurassic dinosaurs is still being written, and the chapters ahead are likely to be as surprising as those already told. Beyond the fossils themselves, the Jurassic Americas left a legacy in the geological structures that underlie the modern continents. The great river systems that drained the Morrison Basin were in some ways the ancestors of the modern Colorado River drainage system, though of course the specific courses and configurations are completely different. The processes of erosion and deposition that created the Morrison are still operating in the American West today, removing material from the Rocky Mountains and depositing it in the lowlands and basins to the east and south. The landscape is different, transformed by 65 million years of additional history, but the fundamental processes are continuous. In South America, the Jurassic saw the beginning of tectonic processes that would eventually produce the Andes. The subduction of oceanic crust beneath the western margin of South America, The process that today drives the volcanic activity and mountain building of the Andes was already underway in the Jurassic. The early stages of Andean orogeny, the building of the Andes, were just beginning during the period we have been discussing. Over the next 100 million years, they would accelerate, and eventually the Andes would rise to their current extraordinary heights, reshaping the climate and ecology of an entire continent. The living world also carries the legacy of the Jurassic Americas in ways that are only now being fully appreciated. Modern birds, as we have noted, are the direct descendants of theropod dinosaurs, and many of the fundamental features of bird biology, including their air-sac respiratory system, their hollow bones, their feathers, and many aspects of their reproductive and social behaviour, can be traced back through the theropod dinosaur record to animals that lived during the Jurassic Americas. The crocodilians of the modern world are less directly descended from Jurassic American ancestors, but the crocodilian body plan, perfected in the Jurassic waterways, has changed remarkably little in 150 million years. The American alligator in its Louisiana swamp is in many important ways the same animal as the crocodilians that prowled the Morrison rivers. It has had 150 million years to change, and it has changed relatively little, because the body plan that evolved in the Jurassic was so well suited to the semi-aquatic ambush predator lifestyle that there has been little evolutionary pressure to change it significantly. The mammals, our own group, carry a Jurassic legacy that is more indirect but equally real. The small furry mammals of the Jurassic Americas, the creatures that moved through the undergrowth while the great sauropods shook the ground, were the ancestors of all living mammals including ourselves. Their small size, their nocturnal habits, their elevated metabolism, their increasingly sophisticated brains, all of these were characteristics refined during the long Jurassic period of living in the shadows of dinosaurs. We are what we are in part because of what it was like to be a small furry animal in a world of giants. The flowering plants that dominate the modern world were not present in the Jurassic Americas, but the vegetation of the Jurassic, the conifers and cycads and ferns, set the stage for their eventual appearance. The ecological relationships between plants and animals, between vegetation and soil, between forest and climate, that were established and refined during the Jurassic, provided the framework into which flowering plants would eventually insert themselves when they appeared in the Cretaceous. The world was ready for flowers long before flowers appeared. And the insects of the modern world, in all their extraordinary diversity, owe much of that diversity to evolutionary radiations that began or accelerated during the Jurassic. The beetles, the flies, the wasps, the ants, all of these groups were diversifying through the Jurassic and early Cretaceous, their evolutionary trajectories set by the environments and opportunities created by the Jurassic world. When flowering plants eventually appeared and offered new opportunities for pollination and herbivory, it was insects whose diversity and adaptability allowed them to exploit those opportunities most completely, producing the intimate coevolutionary relationships between plants and insects that characterize so much of the modern natural world. The Jurassic Americas, in other words, are not simply gone. They are encoded in the living world around us, in the bones of birds and the behavior of crocodiles and the biology of mammals and the structure of forests and the diversity of insects. We are, in a very real sense, living in the world that the Jurassic Americas helped to create, the world that was set in motion by the rifting of Pangaea and the great radiation of the dinosaurs and the development of the complex ecosystems of the Morrison and the South American Jurassic basins. We are the inheritors of this ancient world, and knowing something about what that world was like, feeling some sense of its scale and its richness and its extraordinary life, seems to us a worthy and important thing. Not just as an intellectual exercise, though it is that, but as an emotional and imaginative experience that deepens our sense of our own place in the story of life on Earth. The Jurassic Americas were remarkable. They were full of life and wonder and creatures of unimaginable size and strangeness. They existed for millions of years, in a world so different from ours that a traveller through time would struggle to recognise it. And then they were gone, transformed by the slow grinding of geological time into the different world of the Cretaceous, and eventually into the world we know today. But the story did not end when the Jurassic ended. The story of life never ends, not while a single living cell divides somewhere on this ancient planet. It continues, always, in new forms and new configurations and new possibilities that the Jurassic world could not have anticipated any more than we can anticipate what will come after us. We are part of the story, all of us. Everything that lives is part of the story. And the story goes back further than we can easily imagine, to world upon world upon world, each one complete and extraordinary and gone, and each one contributing something to the world that came after. The Jurassic Americas are one of those worlds, and tonight we have visited them. Let us go back one more time, back to the ancient world, back to the warm and extraordinary land that was once the Americas before it knew that name. Let us go back not to study, not to analyse, but simply to be present in that place, to feel what it feels like to stand at the edge of a Jurassic river as the day is ending and the ancient world is settling into its night. The river is wide here, in this late Jurassic evening, and it moves slowly, carrying its cargo of fine suspended sediment with a gentle persistence that has been building this floodplain for tens of thousands of years, grain by grain, layer by layer. The water is the colour of pale tea where it catches the last light, and darker, almost bronze, where it runs in shadow beneath the overhanging vegetation of the bank. The vegetation along the bank is dense and green and strange to modern eyes. Horsetails as thick as your arm grow in stands along the water's edge, their jointed stems and whorled branches reaching upward in patterns that are ancient beyond reckoning, because horsetails have been growing like this for over 300 million years, since long before the first dinosaur took its first step. Ferns spread their fronds over the darker ground beneath the bank's overhang. Their green so deep it is almost black in this light. And behind all of it, the conifers rise, the greater Araucaria relatives and their companions, their canopies 50 metres above creating a roof of green that the last sunlight filters through in long, angled beams. The sounds are settling into their evening register. During the day, the floodplain was a place of constant motion and sound. The deep vibrations of large animals moving, the calls of smaller dinosaurs in the forest margin, the splashing of crocodilians in the shallows, the ceaseless insect chorus that underlaid everything. Now, as the light softens and the temperature begins to fall from its daily peak, things are quieting. The large herbivores have moved away from the open floodplain toward the shelter of the forest margins. The thermals that carried the pterosaurs in wide circles overhead have collapsed with the cooling air, and the sky is empty of wings. What remains is a kind of profound, particular quiet, the quiet of ancient places, the quiet that comes when you're somewhere that has not been altered by human activity, somewhere that is purely and completely itself. The river talking softly over a shallow gravel bar downstream, the small sounds of insects in the vegetation, the occasional distant call from somewhere in the forest, a sound that has no modern equivalent, the call of an animal whose closest living relatives are birds, but that is not quite a bird, not yet. The sky above is enormous and clear, the kind of sky that only exists far from any light pollution or atmospheric disturbance. The early stars are beginning to appear, not the stars we know, their constellations rearranged by the long, slow, proper motion of the stellar neighbourhood through the galaxy over 150 million years, but stars nonetheless. The same stars, the same great galaxy, the same universe. And for a moment, looking up at that ancient sky from this ancient place, the distance between now and then collapses. The universe does not know that 150 million years have passed. The stars are indifferent to the dinosaurs below them, as they are indifferent to us. Somewhere on the floodplain not far away, a small bipedal dinosaur is moving through the last light. It is perhaps a metre tall, quick and alert, its head turning with that bird-like precision that we now understand is directly ancestral to the head movements of modern birds. It is hunting insects in the fading light, each movement deliberate, each step placed with care on the uneven mud. It catches something, swallows, pauses, catches something else. It is entirely absorbed in the business of living, entirely present in this moment, unaware of its own significance, unaware that its descendants will one day rule the sky. This is life as it always is, at its most fundamental level. Not cosmic drama, not the great sweeping narratives of geological time. Just an animal, alive, doing what it needs to do to remain alive, in a place that is beautiful and ancient and full of quiet wonder. In the tree line at the edge of the floodplain, the small mammal has emerged from its daytime shelter, in a hollow beneath a root. It is beginning its nightly rounds, moving with the quick, perpetually alert energy of a creature that is always simultaneously hunter and prey. Its nose works the air, Its large eyes gather the last scraps of light. It navigates a world of enormous scale relative to its own body, a world in which every fallen log is a landmark, every patch of bare soil a potential hunting ground, every shadow a potential threat. And it lives. Night after night, generation after generation, through all the geological upheavals and climate changes and extinctions and radiations that the Jurassic world will yet produce, the small mammals survive. They carry their lineage forward through time with the quiet persistence of creatures that have learned the ancient lesson that size and strength are not the only paths to survival. Patient adaptability, high intelligence relative to body size, flexible diet, careful investment in offspring, all of these things are the mammalian strategy, and they will carry it to extraordinary places in the fullness of time. But not tonight. Tonight it is just a small warm creature in a big dark world, doing what it must to survive, and there is something enormously touching about that. Something that connects us to it, across all the distance of time and transformation. Because that is what we are too at the deepest level. Small warm creatures in a big universe, doing what we must to survive, and finding in the time we're not spending on survival the capacity to wonder at the world we live in. The river is darker now. The stars are brighter. The last of the daylight has pooled in the western sky, a deep blue fading to black at the zenith, and in the east the darkness is complete and full of stars. In the forest the night insects have begun their different, slower chorus. Somewhere in the distance something large is drinking, the sound carrying across the still air with a clarity that the busy daytime soundscape would have covered. This is the Jurassic Americas on a summer night, 150 million years ago, a world complete in itself, a world that does not know it is ancient, because for every creature living in it, it is simply the world, the only world, the whole world. Let this world hold you for a moment. Let the ancient river flow. Let the stars turn overhead in their Jurassic configurations. Let the small mammal move through the leaf litter on its nightly rounds. Let the great forms of the distant sauropods be present somewhere out there in the dark, their breathing slow and vast, their bodies like living mountains resting in the warmth of the Jurassic night. You are very far from that world, and you are part of it. Both things are true. One of the things that makes the story of the Jurassic Americas so remarkable is not just the story itself, but the fact that we know it at all. The Jurassic Period ended 145 million years ago. No human being has ever seen a living Jurassic dinosaur or walked through a Jurassic forest or looked out across a Jurassic sea. Every detail in everything we have described tonight is inferred, reconstructed, built up painstakingly from physical evidence preserved in rock. This is the extraordinary project of paleontology and its allied sciences, the recovery of vanished worlds from the clues they left behind. And the clues, remarkable as it may seem, are actually quite numerous and quite revealing. They just require the right kind of reading. The bones themselves, of course, are the most obvious evidence. When an animal dies under conditions that allow its body to be buried rapidly in fine sediment, shielded from the scavengers and the decomposers that would otherwise reduce it to nothing, the hard parts of the body, the bones and teeth, and sometimes shells, can be gradually replaced by mineral material over millions of years in a process called permineralization. The resulting fossil is not bone anymore, in a strict chemical sense. It is rock in the shape of bone, a mineral replica so detailed that it preserves the texture of the original bone surface, the microscopic structure of the bone tissue, sometimes even cellular level detail. From bones alone, a skilled paleontologist can reconstruct an extraordinary amount about a living animal. The shape and proportions of the body, the attachment points of muscles, from the scars and ridges on bone surfaces where tendons connected, the probable range of motion of joints, the presence and arrangement of air spaces in the skeleton, growth rates, inferred from growth rings in bone cross-sections similar to the growth rings in trees, the diet, suggested by tooth shape and wear patterns, the sensory capabilities, suggested by the size and shape of brain endocasts, the natural casts of brain shape that form in the skull cavity. But bones are only the beginning. Trace fossils, the physical evidence of an animal's behavior rather than its body, provide information that body fossils cannot. Footprints, preserved in what was once soft mud, tell us about an animal's gait, its speed, Whether it moved alone or in groups, whether it held its body horizontally or more upright, how its weight was distributed across its feet. Morrison Formation trackways have been found that allow paleontologists to calculate the walking speeds of specific sauropods, to determine the spacing between individuals in a moving herd, to identify places where a predator's tracks intersected with a prey animal's tracks. Skin impressions, preserved where a dead animal came to rest on a muddy surface and left a cast of its skin before the soft tissue decomposed, tell us about the external covering of animals whose bones suggest nothing about what their outer surface looked like. Feather impressions on some theropod specimens tell us not just that feathers were present, but details of their arrangement and sometimes their colour, revealed by microscopic structures called melanosomes that preserved the pigment-producing cells. Stomach contents, preserved in the ribcage region of well-preserved specimens, tell us directly what an animal ate, and sometimes reveal quite specific information about feeding habits. The presence of gastroliths, polished stones, swallowed and retained in the stomach to help grind food, in some sauropod specimens has contributed to debates about their digestive strategies. The specific fish species found in the stomach contents of ichthyosaur specimens has told us something about the prey choices of these ancient marine predators. Geochemistry provides another window into the past. The chemical composition of fossil bone and tooth material records something of the chemistry of the animal's body and environment during its lifetime. Isotope ratios in tooth enamel can reveal where an animal lived, whether it migrated seasonally, what temperature its food and water were at, and sometimes even what it ate. The carbon and oxygen and strontium isotopes preserved in ancient bone and tooth have told us things about Jurassic dinosaur ecology that direct observation of the animals could not have revealed without years of study. Ancient soils, the paleosols preserved in the rock record, are another remarkable source of information. The colour, texture, mineral composition, and the presence of root traces, burrows, and chemical signatures in ancient soils can reveal the climate under which they formed. Wet soils look different from dry soils in specific ways that are recognisable in the rock record. Warm soils show different weathering products than cool soils. The degree of development of a paleosol reflects how long the surface was stable before being buried by new sediment. Pollen and spores, preserved in ancient sediments, give us detailed pictures of the plant communities that no larger fossil could provide. Plant fossils, large and obvious, tell us what specific plant species looked like and where they grew. But a complete picture of the vegetation requires knowing which plants were present, even where their large fossils are absent, and pollen is the answer. Pollen grains are extraordinary in their ability to survive in sediments for millions of years, and their distinctive shapes allow individual species to be identified under a microscope. A sediment sample containing pollen can tell a botanist more about the ancient vegetation than a collection of leaf impressions. All of this evidence is drawn together by the scientists who study these ancient worlds and synthesized into the reconstructions and narratives that allow us to imagine what it was like to stand in a Jurassic landscape. The reconstructions are not perfect. They contain uncertainties and inferences and educated guesses. The colours of dinosaur skin and the specific sounds of their vocalizations, for instance, are largely beyond recovery, constrained in some cases by indirect evidence but ultimately unknown in their specifics. But the big picture, the general shape of the world, the sizes and relationships and behaviours of the animals, the character of the vegetation and climate, the dynamics of the ecosystems, all of this is accessible to scientific investigation, and the picture it reveals is extraordinary in its richness and detail. Every year, new discoveries add new details. New fossil sites yield new species. New analytical techniques extract new information from existing specimens. New theoretical frameworks allow existing data to be interpreted in new ways. The story of the Jurassic Americas is not finished being told. It is growing richer and more detailed year by year, as more bones come out of the rock and more scientists bring new tools and new questions to the material. The next great discovery is out there somewhere, in the Badlands of Wyoming or the remote canyons of Patagonia or the coastal cliffs of Portugal, waiting for the right person to find it. This is one of the things that makes paleontology such a remarkable and rewarding science. The subject matter is ancient and gone, but the science itself is very much alive and ongoing. The Jurassic Americas are being studied right now, at this moment, in laboratories and field sites around the world. The story is being extended, deepened, revised, and enriched by the work of thousands of scientists in dozens of countries. The dialogue between the past and the present that is paleontology is continuous and productive. And it is, at its best, an act of imagination as much as an act of science. Putting the bones and the chemistry and the tracks and the pollen together into a coherent picture of a living world requires imagination of a disciplined and informed kind. It requires the ability to look at a fossil and see not just an object but a life, not just a specimen but an animal that ate and moved and breathed and possibly feared and possibly loved in its own ancient fashion. This imaginative capacity, combined with rigorous scientific method, is what allows the dead past to live again in our minds. And that, perhaps, is the most important thing we can say about the Jurassic Americas. Not the specific details of which species lived where, not the exact measurements of the largest sauropods, not the precise timing of the geological events that shaped the continent, but the simple, extraordinary fact that it is recoverable, that across a gulf of 150 million years, using nothing but rocks and careful thought and scientific imagination, we can stand in that ancient landscape and see it and feel something of what it was. That capacity, the capacity to reach across deep time and bring back vanished worlds, is one of the most remarkable things about human beings. We are the only creatures in Earth's 4 billion year history who have ever looked back at the deep past and tried to understand it. We are the only species that has ever wondered about the world before its own time and worked out a method for recovering something of that world from the physical evidence it left behind. That is something extraordinary. It is part of what makes us human, and it connects us to every world that has preceded this one. The Jurassic Americas are gone, but tonight, in your imagination, you have been there, and that is a remarkable thing. There is one more dimension to the story of the Jurassic Americas that deserves our attention before we close. It is the dimension of place, of the relationship between the ancient landscape and the modern one. Because the Jurassic Americas exist not only in the deep time of geological history, they exist, in fossilized form, in the very land that people live on and walk across and drive through today. If you have ever driven through the American Southwest, through the dramatic canyon country of Utah and Colorado and Arizona, through the sweeping badlands of Wyoming and South Dakota, you have driven through a landscape shaped by deep time. The red and orange and cream and lavender bands of colour in the canyon walls are sedimentary layers, each one a different moment in geological history, stacked by the patient accumulation of sediment over hundreds of millions of years. Some of those layers are Jurassic. When you stop at a viewpoint in Arches National Park or Canyonlands and look out across the layered stratigraphy of the canyon walls, you may be looking at Morrison Formation sediments. The dark reddish-brown layers, the cream-coloured sandstones, the occasional grey mudstone bands. These are the remains of the Jurassic floodplain, the very ground that Brachiosaurus walked on and Allosaurus hunted across, compressed and lithified by time and pressure into the rock before your eyes. At Dinosaur National Monument on the Colorado-Utah border, there is a quarry wall where the exposed face of a sandstone ridge contains hundreds of dinosaur bones preserved in place. A cross-section through what was once a sandbar in a Jurassic river, where the bones of animals washed downstream and came to rest in a mass accumulation. Standing at the railing and looking at this wall of ancient bones embedded in ancient stone, you are looking directly into the Jurassic. Not a reconstruction, not a reproduction. The actual bones in the actual rock from the actual river, 150 million years ago. Utah's Cleveland Lloyd Dinosaur Quarry, as we mentioned earlier, has produced more Allosaurus specimens than any other site in the world. The bones come out of a mudstone lens that is reached by a short trail through the red desert. The landscape around it is dry and beautiful, the kind of high desert landscape that feels ancient even on a human timescale. And in the rock just below the surface, the bones of dozens of individual Allosaurus animals, along with bones of several other Morrison species, wait in the dark for the next excavation season to bring them into the light. In Wyoming, the Como Bluff area was one of the great early sites of Morrison Formation paleontology, the place where the famous bone wars of the late 19th century were partly fought, as rival paleontologists Othniel Charles Marsh and Edward Drinker Cope sent competing teams to dig out the extraordinary bones eroding from the hillsides. The bones they found transformed our understanding of the deep past and established the basic outline of the Morrison fauna that we have been describing tonight. And the same beds that produced those first great discoveries are still there, still eroding, still yielding new material to new researchers with new questions and new tools. In South America, the Ishigualasta Provincial Park, that Valley of the Moon where the story of the first dinosaurs was written in the rock, is now a UNESCO World Heritage Site, recognized for the extraordinary importance of its paleontological resources to the understanding of the history of life. Visitors can walk through those alien grey and lavender badlands today, and if the light is right and the eye is trained, they can see fragments of ancient bone eroding from the hillsides, the last physical traces of animals that walked here 230 million years ago. The Neuquén Basin of Patagonia, that extraordinarily rich repository of Jurassic and Cretaceous dinosaur material, is less visited by tourists, but equally remarkable in terms of the sheer density and quality of the fossils it contains. New species are described from this region at a rate that keeps paleontologists busy, and the infrastructure for paleontological work here has grown steadily as Argentina has developed its fossil record as both a scientific resource and a source of national pride. These places are not just scientific sites, they are sacred sites in a secular sense. They are places where the distance between the present and the deep past collapses, where you can stand on ground that was once a Jurassic riverbed or a late Triassic floodplain and feel, however briefly and imperfectly, the weight of geological time beneath your feet, where the gap between the world of the living and the world of the fossil is as thin as the layer of rock between the surface you stand on and the bones preserved a few meters below. The Americas that the Jurassic dinosaurs inhabited are buried beneath the Americas we know today, separated from us by 150 million years of geological change and 5 kilometers of rock in some places, much less in others where erosion has cut down close to the ancient surfaces. The land is continuous. It is the same land, just at a different moment in its long history. The rocks that lie beneath your feet wherever you are in the Americas were there in the Jurassic, or at least their precursors were, part of the same grand geological story that has been running since the planet formed. There is something deeply grounding about this, about knowing that the land you stand on has a history that extends far beyond human memory, far beyond human civilization, far beyond the human species itself, that the ground beneath your feet has been walked on by creatures that we would find unrecognizable in a world that was profoundly different from our own. That deep time is not an abstraction or a concept confined to geology textbooks. It is present everywhere, encoded in the rocks, waiting to be read by those who know how. The Jurassic Americas are there, beneath the surface, everywhere in the western part of North America and across much of South America, in the Morrison Basin, in the Neuquén Basin, in the ancient Triassic sediments of the Argentine desert, waiting, patient as stone, ready to yield their secrets to anyone with the skill and the curiosity and the time to look. And in looking, we connect ourselves to something vast and ancient and extraordinary. We participate in the great human project of understanding where we come from, not just in the biological sense, but in the deepest geological and cosmological sense, of knowing our place in the universe not just in space but in time, of recognizing that we are temporary inhabitants of a world that has been many other worlds before it became ours. The dinosaurs of the Jurassic Americas are our deep ancestors in the most fundamental sense, not in the biological lineage sense, though our mammalian lineage was there alongside them, but in the sense that the world they lived in is the world we are the inheritors of. Their world became our world through a long chain of geological and biological events, and knowing their world is, in a strange and profound way, knowing part of ourselves. So when you think of the Jurassic Americas, think not just of ancient monsters and vanished worlds. Think of home. Think of the deep history of the land we live on. Think of the extraordinary patience of the rock that has kept these secrets for 150 million years, waiting for us to develop the curiosity and the tools to ask the right questions. Think of a small furry animal moving through the undergrowth of a Jurassic night, carrying within it the seeds of everything we would eventually become. Think of the ancient river, still flowing in the rock beneath our feet. Think of the great neck of a sauropod moving through the amber light of a Jurassic afternoon, and know that you are looking at something real, something that happened, something that was. And so we have come at last to the end of our journey through the Jurassic Americas. It has been a long journey. We have travelled 230 million years into the past and back again. We have stood in the late Triassic river basins, where the first dinosaurs took their first tentative steps toward dominance. We have watched a supercontinent tear itself apart and birth two great oceans. We have walked through the forests of the Morrison Formation, under the improbable shadows of animals that weighed more than any living land creature. We have looked out across ancient seas where giants moved in the warm green water. We have traced the slow divergence of North and South American faunas as the continents drifted apart. And we have stood at the edge of the Jurassic, watching the last light fall on a world about to become something new. Now let this ancient world fade slowly, gently, like the light at the end of a long summer day. Let the sound of the Jurassic River grow softer in your mind. Let the great shapes of the sauropods dissolve back into imagination, back into the warm darkness from which they came. Let the smell of ancient mud and ancient conifers and ancient water drift away on a wind from 150 million years ago. The rocks are settling, the stars are turning, the small warm creature in the leaf litter has found its shelter and is still. The great predator in the forest has made its kill and is resting. The river is carrying the day's sediment slowly toward the ancient sea. Everything is calm in the Jurassic Americas tonight. And you are here, in your own moment, your own time, your own corner of this old planet's long story. Let the weight of geological time be a comfort rather than a burden. Let the knowledge that this world has been so many worlds before and will be so many more release you from the urgency of the present moment. Let the ancient stillness of the deep past settle over you like the fine sediment settling at the bottom of a Jurassic river. You are part of a 4 billion year story, and tonight you rest in it. The Jurassic Americas are resting too in their permanent sleep of stone, the bones in the rock, the footprints in the